In 1974, two physicists found a description of gravity while looking for something else. They were studying the force that holds an atomic nucleus together, and their theory was already in trouble. It did not describe that force well, but when they solved the equations, one particle kept appearing that no one had put there. Massless. Spin 2. Those are the exact properties a particle carrying gravity would need to have. A theory built for one force had produced the fingerprint of a completely different one. That single particle became the first clue to what many people now call the theory of everything. It was never designed to explain the universe. The explanation arrived sideways. Tonight we follow that clue through hidden dimensions and a picture of reality stranger than the people who found it expected. Gravity grows stronger as two things move closer together, and nobody has ever found the place where that stops. The sentence sounds harmless. It is the reason anyone needed a theory of everything at all. Say we set two small objects on a table with a gap between them. They pull on each other, far too faintly to feel, but they do. Now we slide them halfway together. The pull becomes 4 times as strong. Halve the gap again, and it is 16 times. 10 halvings, and the pull has grown by about 1,000,000. Nothing in the arithmetic complains. We can go on halving for as long as we have patience. 46 halvings carries us from the width of a hand down to the width of a proton, and by then the pull between those two objects has grown by something like 5 billion times. Isaac Newton wrote this in one line. The force equals big G times the first mass times the second mass divided by the distance squared. The distance sits at the bottom of that fraction, which is where the trouble lives. As the gap shrinks toward nothing, the answer does not become large. It stops existing. Albert Einstein said the same thing in a gentler language, and the trouble came with him. In his account, mass and energy bend space and time, and the bending is what we feel as weight. His field equations hold the bending on one side and the mass and energy on the other. Curvature on the left, contents on the right. When the contents are pressed into no space at all, the left side of that equation has nowhere left to go. Quantum mechanics is usually the thing that rescues physics from an answer like that. It did the job 3 times already. Electricity and magnetism, the force that holds a nucleus together, and the force that lets one kind of particle turn into another. All 3 were pulled into quantum form, and the results are the most accurate work our species has produced. An electron behaves like a very small magnet. The strength of that magnet has been measured, and it has also been calculated from the rules of quantum electrodynamics, with no magnets involved anywhere in the calculation. The measured value and the calculated value agree to roughly 12 digits. Scaled up, that is like working out the distance from here to the moon and being wrong by less than the width of a hair. The reason that works comes down to a single number, written as alpha, and close to 1/137. A quantum answer is never finished in one step. There is a first rough answer, then a correction to the correction, and so on. In electromagnetism, alpha shrinks each step by roughly 100. The second correction is 100 times fainter than the first. The third is fainter still. After 4 or 5, We have passed the point where any instrument could tell the difference, so we stop, and the answer is as good as the world can check. The quantum rules insist on one more thing, and it ties the two halves of this together. Nothing can be pinned into a small space without its energy rising. The tighter the space, the more energy is loose inside it. This is not a shortcoming of our instruments. It is how small spaces behave. So closing the gap between two objects and raising the energy inside that gap are not two different acts. They are one act, described twice. Gravity has no alpha. What multiplies each step is not a constant at all. It is the energy involved in whatever we happen to be doing, measured against one fixed energy that falls out of the constants themselves. That fixed quantity is Planck's, and its matching length is small in a way that resists comparison. If the Planck length were widened to a single millimeter, a proton would come out about 11 light-years across, roughly 2.5 times the distance from the Sun to the next nearest star. So the size of each correction depends on how hard we are pushing. Down here, in a room, with a body on a bed and a planet underneath, the energies are so far below that fixed value that the second step in the calculation is already too faint to matter. The first rough answer is the whole answer, and the theory behaves beautifully. This is not an approximation anyone apologizes for. It is why weight works. Someone did carry the calculation further, and the result is easy to miss. In the 1990s, John Donahue worked out the first quantum correction to Newton's law, a real extra term built from Planck's constant, big G, and the speed of light. At the size of an atom, that term changes the pull between two masses by about 1 part in 10 to the 50th. A decimal point, then 49 zeros, then the first digit with any meaning in it. The first time I followed this through, I kept waiting for the part where the theory gives a wrong answer. That part never comes. What happens instead shows up further along. In 1974, Gerard Hooft and Martinus Veltman took gravity by itself, with no matter anywhere in the picture, and pushed the calculation to its first level of correction to see whether it would hold. It held. The pieces that were expected to blow up canceled one another and left something clean. That result kept a certain kind of hope alive for about 10 years. In the middle of the 1980s, Mark Goroff and Augusto Sagnati went one level deeper, and the canceling stopped. A quantity came out infinite, and it arrived carrying a coefficient. 209 over 2,880? Nobody had been hoping for a number like that. Years later, another physicist redid the whole thing by a different route and found the same fraction waiting for him. An infinity on its own is survivable. Electromagnetism throws them out constantly, and they are absorbed by adjusting a measured quantity, which sounds like cheating until you see that it only ever has to be done a fixed number of times. Two numbers go into quantum electrodynamics, and the theory hands back everything else. Gravity does not offer that arrangement. Every new level of correction produces a new kind of infinity, and each one needs its own measured number to absorb it. Nobody can calculate those numbers. They would all have to be measured, and the list does not end. In practice, it plays out like a conversation that never closes. We ask how gravity behaves at some enormous energy. The theory says it can tell us as soon as we go and measure a quantity nobody has ever measured. We measure it and come back. The theory thanks us and asks for the next one. so the failure has a shape most descriptions leave out. The theory is not wrong. Ask it something easy, and it answers correctly. Ask it something harder, and it answers correctly again, but first it wants one more number from us. Ask it about the beginning of the universe, or the middle of a black hole, and it wants an endless supply of them. Those two places are the reason any of this matters. Everywhere else, including this room, the gap between two things never gets small enough to force the question, and both descriptions of gravity run side by side without ever meeting. A body resting on a bed is held there by curvature. Every atom in that body keeps its shape by quantum rules. Both are true at once tonight, in the same few cubic feet, and nothing about the arrangement feels strained. Albert Einstein spent his last 30 years on a nearby problem. The blackboard in his Princeton office was still covered with it on the day he died, in April 1955. He was trying to join gravity to electricity and magnetism, and the two nuclear forces were still being worked out while he wrote. He was also working without the quantum rules, which he never made peace with. The piece that finally moved was not found by anyone thinking about gravity. It came from a group of people staring at a table of numbers from a particle accelerator in California, trying to work out why the particles coming out of it made no sense. So, what were those numbers, and what led one man to reach back 200 years for a piece of mathematics that had nothing to do with physics? The theory of everything started as a formula that fitted a table of measurements, and the formula arrived about 2 years before anyone worked out what it was describing. The order matters, so we will follow it in the order it happened. By the late 1960s, the accelerator at Berkeley had created a problem nobody asked for. It fired protons into liquid hydrogen and photographed what came out, and what came out was new particles, over and over. The count passed 100. Physicists had been naming them with Greek letters and were beginning to run short. None of them looked fundamental. They arrived, lived for a fraction of a second, and fell apart into other things on the list. A physicist in Turin, Tullio Regge, had suggested at the end of the 50s that these objects might be related families rather than separate entries, and that the family resemblance would surface if somebody looked at them in the right variables. Nobody had drawn that picture yet. Then somebody plotted them. Spin going up the page, mass squared going across. Each particle became one dot, and the dots did not scatter. They lay along straight lines, evenly spaced, several parallel families of them climbing at the same slope. Written out, the relationship is that the spin equals a fixed number times the mass squared plus a small offset, and the fixed number came out around 1 in the units particle physicists use. A straight line on a graph is a quiet kind of gift. It says that underneath 100 separate objects, there is one rule doing the work, and the rule is simple enough to draw with a ruler. The line was measured, checked, and not in dispute. What it was telling anyone remained completely open. Nobody could calculate it either, because the theory that eventually explained the inside of a proton had not been written yet. So, a group of physicists made a decision that sounds like surrender and was closer to discipline. They stopped asking what happens during a collision. They kept only what went in and what came out, and they looked for the mathematical relationship between the two. The rules of that relationship were strict, and they hoped the strictness alone would leave only one possible answer. Those rules asked for one function that could do 3 things at once. It had to reproduce the straight lines on the graph. It had to give the same answer whether the particles were treated as incoming or outgoing, so that a single expression covered two collisions that looked nothing alike on a laboratory floor. And it had to blow up in a controlled way at exactly the masses where a particle existed and stay finite everywhere else. Several people had been hunting for that function for a few years. In 1968, a young physicist named Gabriele Veneziano, then at CERN, found one. He did not build it. He recognized it. The function was Euler's beta function, written down in the 1700s, roughly 2 centuries before anyone knew there was an atomic nucleus to have a problem with. In its plainest form, it is a single integral, running from 0 to 1, of one quantity raised to a power, times another quantity raised to another power. The reason it works is something we can see rather than take on faith. The beta function can also be written as a ratio of 3 gamma functions, and the gamma function has a habit. It runs off to infinity at 0 and at every negative whole number, at regular intervals, forever. Feed the collision energy into it in the right place, and those infinities line up at evenly spaced values of mass squared. Each one of them is a particle. The link between an infinity on paper and a real object is not a trick of notation. A swing pushed at the frequency it already wants responds more and more strongly until something gives. A collision does the same. Aim the right amount of energy at it, and the response spikes, because at that energy, a particle can form and hold together for a moment before coming apart. On paper, the spike is an infinity. In a detector, it is a bump on a curve. The infinite family of dots and the straight line they sit on come out of an 18th century integral without being put there. For 2 years, the formula worked, and no one could say what it was a formula for. It matched the data. It described something. Nobody knew what. That is an unusual position for a person to be in. A correct answer with no question attached is not quite a triumph and not quite a mistake, and there was no agreed way to treat it. The answer came in 1970, from 3 people who did not know the others were thinking about it. Yoichiro Nambu in Chicago, Holger Beck Nielsen in Copenhagen, and Leonard Susskind, then in New York, each arrived at the same reading. The formula is what you get when the things colliding are not points. It is what you get when they are short lengths of something under tension. The tension is the whole idea, and it produces the graph in a way we can follow step by step. Take a length of something with constant pull along it, fix nothing down, and set it spinning end over end. Adding energy makes it longer and makes it turn faster, and both of those raise its angular momentum. Work through the relativistic version, and the angular momentum comes out proportional to the square of the total energy. In that solution, the 2 ends travel at the speed of light, which is as fast as the tension can drive them, while the middle barely moves. Which is the straight line exactly. Spin against mass squared, with the slope set by how tight the tension is. So the slope on that graph, measured off photographs of collisions at Berkeley, was quietly reporting a number. Converted into ordinary units, the tension inside these objects comes out somewhere near 15 tons of pull. That is 15 tons held inside a region smaller than an atomic nucleus, in a thing with no thickness at all. The number had been sitting in the data for years, waiting for somebody to read it as a tension instead of a slope. The same slope also set a length. These strings came out about as wide as a proton, near 1 part in 1,000 trillion of a meter. That size was the entire point of the exercise. The model was built to describe the inside of a nucleus, so a string the width of a nucleus was exactly what anyone would have ordered. 6 years later, two physicists would take that number and move it 20 powers of 10 the other way, and the model would stop being about nuclei at all. The mathematics that followed was almost embarrassingly simple. A point particle moving through time traces out a line, and its equations come from the length of that line. A short length of string moving through time traces out a sheet. Nambu and, separately, Tetsuo Goto proposed that its equations come from the area of that sheet multiplied by the tension. One dimension up, one word changed. Length becomes area, and everything else follows. There is something unusual in how this happened, and it is easy to walk past. The string was not proposed and then tested. The answer existed first, sitting in a formula that fitted the numbers, and the object was worked backwards out of the answer. Physics almost always runs the other way. Somebody imagines a thing, works out what it would do, and goes looking. Here, the thing was inferred from its own footprints. The program that produced it did not last. Within a few years, the approach of refusing to ask what happens inside a collision was overtaken by a theory that answered that question directly, and the whole style of thinking fell out of use. The strings survived their own parent. They were a byproduct of a research program that history quietly closed, and they outlived it by 50 years and counting. And yet the model was in trouble almost immediately, in a way that had nothing to do with fashion. It fitted the graph beautifully, and it was making other predictions at the same time, quietly, without being asked. Some of those predictions were about to be checked. So what was the model saying about a proton hit hard and head-on, and why did almost everyone walk away from it within 5 years? The string model was right about the graph and wrong about the proton, and the experiment that settled it was already running while people were still working out what the formula meant. Nobody set out to test string theory. They were trying to find out what a proton is made of. At Stanford, an accelerator 2 miles long had been built to fire electrons in a straight line, reaching about 20 billion electron volts. Jerome Friedman, Henry Kendall, and Richard Taylor ran the experiments there between 1967 and 1969, and were given the Nobel Prize for them 21 years later. The idea was plain enough. An electron goes into a proton, and the way it leaves is recorded. 2 numbers get recorded for each collision: the angle the electron comes out at and how much energy it has lost. Nothing else. From those 2 numbers, the inside of the proton can be read. The reason that works is old. In 1911, Ernest Rutherford fired heavy particles at a thin sheet of gold and expected them all to pass through with a small deflection because the atom was thought to be a soft spread of charge. A few came straight back. A soft cloud cannot do that. Only something small and hard sitting inside can. The Stanford experiment asked the same question 1 level further down. The string model had already committed itself on this point, and nobody had chosen to. A string has size, and it has give. When an extended floppy object is hit hard, most of the energy goes into stretching and shaking it, rather than into sending anything sharply sideways. Violent, wide-angle events become rare very fast as you push harder. Written out, the number of such events falls away exponentially with energy, which on a graph is the shape of a cliff. The prediction was not bolted on. It came from the same tension that had produced the straight line in the first place. A proton made of small, hard pieces behaves differently, and the difference is a matter of kind rather than degree. Hard, wide-angle events keep happening. They get rarer as the energy climbs, but only as a simple power of the energy, dividing by a fixed factor each time rather than collapsing. Two curves, one plunging, one sloping. Doubling the energy divides the point particle answer by something like 10. It divides the string answer by many thousands. They are not close to each other, and no amount of adjusting parameters moves one onto the other. The electrons at Stanford came out hard and wide. Far more often than a soft object would allow, they lost large fractions of their energy and left at steep angles, the way Rutherford's particles had come back off the gold. Something small was in there, and it was solid enough to hit. The experimenters then ran the machine at one energy and drew a curve. They ran it at a higher energy and drew the curve again. The curve did not move. When the results were written in terms of a single ratio, combining the energy lost and the sharpness of the collision, the whole family of measurements collapsed onto one line, and the energy of the beam dropped out of the answer entirely. James Bjorken had predicted this. It is called scaling. The ratio has a name, written as x, and its meaning is physical. It is the fraction of the proton's momentum carried by whichever piece the electron happened to strike. With enough collisions, the curve of x reports how a proton shares its momentum among its contents. A proton with 3 pieces inside shares it 3 ways, and the measurements agreed. A response that stops depending on how hard you push is telling you something specific. It means the electron is no longer interacting with the proton at all. It is bouncing off one small thing inside the proton, and that small thing has no size of its own for the beam energy to compare itself against. Murray Gell-Mann and George Zweig had proposed such objects in 1964, mostly as a way of tidying the bookkeeping, and had been careful not to insist they were real. Richard Feynman worked out what the scattering would look like if they were. Stanford had found them. The way this gets told, there was a moment when the string model was refuted. There was no such moment. Papers kept appearing for years, and the people writing them were not confused about the data. What happened was slower and more ordinary. A question that had looked like the central problem in physics turned into a question with a known answer, and the answer belonged to somebody else. That answer arrived properly in 1973. David Gross, Frank Wilczek, and David Politzer worked out that a particular kind of field theory does something no theory had been expected to do. Its force gets weaker the harder you probe. The strength of the interaction is not a constant, but shrinks as the energy rises, falling off roughly as 1 over the logarithm of the energy. Slowly, but without limit. Push hard enough, and the quarks inside a proton stop noticing each other, which is exactly why an electron arriving at high energy finds them behaving like free, small, hard objects. Quantum chromodynamics explained the scaling, explained why nobody had ever caught a quark on its own, and did it with point particles and a field theory of the ordinary kind. It was not more beautiful than the string model. It was more correct in the only way that settles anything. What followed was quiet. The field emptied. Graduate students were advised to work on something else, and most of them did. By the mid-70s, the number of people still working seriously on strings had fallen to a handful, scattered across a few institutions, corresponding with each other because there was no longer a community to speak to. Nobody was persecuted, and nothing was forbidden. The subject simply stopped being the place where anything was happening. And then, 20 years later, something happened that I still find difficult to be neutral about. Physicists began computing the energy it takes to separate two quarks inside a proton, using the theory that had won. The answer comes in two pieces. Close in, there is a term that falls off with distance in the familiar way, like electric attraction. Further out, there is a second term, and that term rises in direct proportion to the separation. Pull the quarks twice as far apart, and the stored energy doubles. Pull them 10 times further, and it grows tenfold, with no sign of easing. An energy that rises in step with length is the signature of one thing only. Something with constant tension is being stretched. The coefficient in front of that term has a name in the technical literature, and the name is the string tension. Its measured value sits close to the number that had been read off the slope of the reggae graph years before anyone knew what the slope was for. The energy field between two quarks organizes itself into a narrow tube, and that tube behaves like a piece of string. The same picture answers a question that had bothered people for a decade. Stretched far enough, the tube does not thin out and let the quark go. It holds enough energy to make new particles, snaps, and puts fresh ends on the two broken halves. Pulling on a quark produces more particles instead of a loose quark every single time, which is why nobody has ever held one. So the theory that ended string theory as a description of the nucleus contains a string inside it. Not as a foundation, and not as a fundamental object. As something that forms, at low energies, out of a field made of point particles. The picture had been the right picture at the wrong level of description. None of that was known in 1973, and none of it would have saved the program if it had been. The handful who stayed were not staying because they expected a vindication. They stayed because the mathematics was still doing things they could not explain, and because the wreckage of the model contained a small number of features nobody had managed to get rid of. One of them was a particle that appeared to travel in a way nothing is allowed to travel. Another had no mass at all and refused to leave. So, what were those leftover defects, and why did the first one turn out to have nothing to do with speed? The first defect was a particle whose mass came out as a negative number when squared, and almost everything the name suggests about it is untrue. The mathematics is not in doubt and never was. What the mathematics was saying took a while to hear correctly. The negative number is not hidden. A string under tension can vibrate in a whole family of patterns, and each pattern carries a definite amount of energy, so the theory hands back a ladder of possible particles rather than one. The rungs are evenly spaced in mass squared, which is where the straight line on the Berkeley graph came from. Written out, the mass squared of a state equals the number of units of vibration it carries, -1, divided by the same constant that fixed the tension. The subtraction is the whole trouble. Counting up the ladder is simple enough. Counting down runs into a problem. The lowest rung of all does not sit at 0. It sits one full step below it. A mass squared below 0 looks harmless until it meets the equation that governs motion. In relativity, the energy of a thing is fixed by its momentum and its mass together, written as energy squared equals momentum squared times the speed of light squared plus mass squared times the speed of light to the fourth. Feed a negative mass squared into that and solve for how fast the object moves, and the answer comes out above the speed of light. Gerald Feinberg had already given such an object a name a year earlier, in 1967. He called it a tachyon, from the Greek for swift. If that word has reached you before tonight, it probably arrived through a film or a novel, carrying messages backwards through time and undoing causes with their effects. That version has almost nothing to do with what the equations were reporting. The mistake sits in one assumption, made so early that it rarely gets examined. The equation was read as though it described a small object traveling somewhere. In these theories, particles are not small objects traveling somewhere. A particle is what a field does when it wobbles gently around a resting value. The mass term does not set a speed. It sets the shape of the energy surface the field is sitting on, and near the resting point that surface goes like 1/2 of the mass squared times the field squared. Two shapes come out of that expression, and the sign decides which. With the mass squared positive, the surface is a bowl. A marble placed in a bowl and nudged rolls back and forth around the bottom forever, at a rate set by how steep the bowl is. Those oscillations are the particle, and the steepness is its mass. With the mass squared negative, the same expression turns the bowl upside down. A marble balanced on a dome does not oscillate. It leaves. So the negative number was never a claim about speed. It was a message about where the calculation had been set up. Someone had chosen a starting point, assumed the theory would sit quietly there, and expanded everything around it, and the sign was reporting that the chosen point was a summit rather than a valley. Nothing about that involves outrunning light. When the field does roll, the rolling spreads through space at the speed of light or slower, like everything else. The word carried a promise the mathematics never made, and it carried it for 50 years. The thing being described is stranger than the story that replaced it, and quieter. A theory was telling the people who wrote it that they had begun in the wrong place. Working out where it should have begun instead took nearly 30 years. Toward the end of the 1990s, Ashok Sen showed that in the open string case, the field does roll, that it rolls to a stable resting place, and that the object the string was attached to comes apart on the way. The negative number had been pointing at a real event the whole time. Not a particle moving faster than light, a thing falling apart. There was a second defect, and it was worse, because it could not be argued about at all. The vibrating patterns of a plain string all produce particles whose spin comes in whole numbers. 0, 1, 2, and upward. Every particle that matter is built from, every electron, every quark, carries a spin of 1/2. A theory made of plain strings can describe forces. It cannot describe anything to be made of. And there was a third, which is the one people remember. In 1971, Claude Lovelace worked out how many dimensions the theory needs in order to hold together, and the answer was 26. 25 of space and 1 of time. Lovelace, who had become a physics professor without ever finishing a doctorate, was not making a proposal about reality. He was reporting the value at which a certain inconsistency cancels. Where the number comes from is one of the odder corners of this subject. A string has infinitely many ways of vibrating, and quantum rules give every one of them a small baseline energy that cannot be removed. Adding them all up gives 1 plus 2 plus 3, and onwards forever. Handled with the right care, that sum has a finite value, and the value is -1/12. That fraction is what pushes the bottom rung of the ladder below zero, and the number of dimensions is what sets how hard it pushes. Set the dimensions to 26 and the arithmetic balances. Set them to anything else and the theory contradicts relativity. Nobody had any account of where those extra dimensions might be sitting. That question would wait another 14 years for a serious answer. So, by 1971, the position was uncomfortable and completely clear. The theory had no matter in it, needed 22 more dimensions of space than anyone had ever seen, and began its own ladder of particles one step below zero. None of those were errors in the calculations. All three came out of the same construction. The repair arrived from Pierre Ramond, who asked what would happen if the string carried something besides shape. Alongside the vibrations that move it through space, he added a second set that describes how it twists internally, of the kind that gives a particle half-integer spin. André Neveu and John Schwartz worked out the matching piece for the whole number states. Suddenly, there were fermions in the theory, which meant there could be matter in it. What came with them was not asked for. The two kinds of vibration, the ones that shift the string and the ones that twist it, turned out to be paired, so precisely that each pattern of one has a partner in the other. A symmetry of that kind, exchanging the two families of particles, is called supersymmetry. It entered this story as a bookkeeping device on the surface. A string sweeps out, and nobody at the time was presenting it as a claim about new particles waiting in an accelerator. The pairing also did the arithmetic a favor. Fermions carry their own baseline energies with the opposite sign, so part of that stubborn -1/12 gets cancelled from the other direction. The bottom rung of the ladder lifts up to zero, and the state with negative mass squared simply is not there anymore. The dimension count that keeps everything consistent falls from 26 to 10. 9 of space, 1 of time. The same year, in Moscow, Yuri Golfand and Evgeny Lichtman had written down a symmetry pairing bosons with fermions in ordinary four-dimensional space, for reasons that had nothing to do with strings. Two groups of people, unaware of each other, arriving at the same structure in the same 12 months, coming at it from opposite directions. That kind of coincidence does not prove a thing is real. It does tend to keep people interested. Something else had happened in the accounting that nobody drew attention to yet. Removing the tachyon had cleaned up the bottom of the ladder, and the rung that now sat at zero was occupied. There was a massless particle down there. In the version of the theory built from closed loops rather than open ends, it carried 2 units of spin, and no adjustment anyone tried would remove it. For a theory of the atomic nucleus, a massless particle is a catastrophe, because the nuclear force reaches only across a nucleus, and a massless carrier would reach forever. So they spent 6 years trying to delete it, and what were they deleting? The particle they were trying to delete was the graviton, and for 6 years its presence was the strongest single argument that the whole theory was wrong. That is not how the story usually gets told. Told properly, it makes the people who wanted it gone look careful rather than blind. The thing sitting on the bottom rung had been named 40 years earlier by a Soviet physicist, Dmitry Blokhintsev, working with Fyodor Galperin in 1934. They were not proposing an experiment. The other 3 forces were understood as particles being passed back and forth, So somebody wrote down what the corresponding particle for gravity would have to be like, gave it a name, and left it there. Nobody has ever detected one. Nobody expects to. Its required properties are short and unforgiving. Gravity pulls on everything with mass or energy, without exception and without regard to charge. And gravity reaches across the space between galaxies. That second fact fixes the mass of the carrier, because in quantum theory, the reach of a force and the mass of the particle carrying it are two ways of saying the same thing. The relationship is one line, and it can be read like a graph. The strength of a force between two objects falls with distance, divided by that distance, and multiplied by a factor that dies away exponentially once the distance passes a certain length. That length is Planck's constant, divided by the carrier's mass times the speed of light. A heavy carrier gives a short leash. A light carrier gives a long one. A carrier with no mass at all removes the exponential factor completely, and the force simply falls off with distance, forever. The nuclear force had already been measured, and it stops. Two protons sitting a nuclear width apart feel it strongly. Move them 10 nuclear widths apart, and it has effectively gone. The particle that carries it, the pion, has a mass that matches that reach almost exactly, giving a leash of about 1.5 times the width of a proton. This was not a preference or an aesthetic. It was a number in a table. So, a massless particle in a theory of the nucleus is not an inconvenience. It is a prediction of a force with unlimited range where none exists. Anyone finding that in their equations would be right to try to remove it. That is what the 6 years were. A string can be made two ways, and the difference decides everything here. It can have two loose ends, like a short length of thread, or the ends can be joined so that it forms a closed loop. Both obey the same tension and the same equations, and they carry entirely different families of particles. On a closed loop, a wave can travel around it in either direction, and both directions are always present at once. The lowest state that combines one wave going each way carries 2 units of spin, and it carries no mass. That state is not an optional feature of closed loops. It is the first thing a closed loop can do. Meanwhile, the open strings, the ones with loose ends, carry states that behave like the carriers of the other 3 forces, so a theory containing both kinds contains both kinds of physics, and neither can be switched off without breaking the other. Removing it meant something specific. The bottom rung of a closed string is not put there by choice, so nobody was hunting for a line to cross out. They were looking for a different version of the theory, a different set of consistency conditions, a different way of counting the vibrations in which that rung came out empty. Several people tried several routes. Every route led back to the same state. The reason is deeper than bookkeeping, and it had been sitting in the literature since the early 60s. Suppose any theory at all contains a particle with no mass and 2 units of spin. For the theory to hold together, for the probabilities to add to 1 and the unphysical states to cancel, that particle has to attach itself to every source of energy in the theory with the same strength for every one of them. No exceptions are permitted. Nothing may be left out. Which is a sentence about geometry wearing the clothes of particle physics. A force that pulls on everything in proportion to its energy with one universal strength is a force that gives every object the same acceleration regardless of what it is made of. That is the statement Albert Einstein began from. Work through the low-energy behavior of such a particle carefully, as Richard Feynman and Steven Weinberg and others did in the 1960s, and the equations that come out are Einstein's field equations. Not something resembling them. So the theory had not produced a particle that looked awkwardly like a graviton. It had produced gravity, complete, with the rule that everything falls the same way already attached. The people trying to delete it were trying to delete general relativity from their equations, without knowing that was what they were doing. In 1974, two physicists at the École Normale Supérieure in Paris stopped trying. Joël Schurk and John Schwartz proposed keeping the massless state and reading it as the graviton. In Japan, working alone and publishing at nearly the same time, Tamiaki Yonya had reached the same conclusion. The proposal has a simple shape. If the theory insists on containing gravity, the theory is not about the nucleus. It is about something else, and the only question left is what scale it belongs to. Answering that took one number: the tension. A string with the tension read off the Berkeley graph is about as wide as a proton, and gravity coming out of such a string would be enormously stronger than the gravity we measure. So the tension goes up, and it goes up until the strength of that massless particle's pull matches Newton's constant. The length that comes out is the Planck length, 20 powers of 10 smaller than where they started. That factor is difficult to hold, so it helps to apply it to something familiar. An orange is about 10 centimeters across. Shrink an orange by the same factor that Schurk and Schwartz applied to the string, and what remains is roughly 1,000,000 times smaller than the nucleus of an atom. The tension climbs by the square of that ratio, which is a factor of about 10 to the 40th. 15 tons becomes a number with 44 digits in front of the decimal point in ordinary units of force. And the theory gave something back for it. Newton's constant stops being a number handed in from outside. It comes out, assembled from the tension of the string and a second quantity describing how readily strings split and join. A theory that begins with one length and one coupling strength produces the strength of gravity as a result, rather than an assumption. Nobody had managed that before, in any framework. It is instructive to set this beside the failure from earlier. In the ordinary approach, gravity has to be inserted by hand, and then the calculation asks for an endless supply of measured numbers and never stops asking. Here, gravity cannot be got rid of, and the calculation stays finite where the other one came apart. Both approaches describe the same universe at low energy and agree with each other there. Where they differ is in what each one is permitted to assume and which of them gets to be surprised. The response to the 1974 papers was almost nothing. Not hostility, and not dismissal in print. Something quieter than either. The theory had just moved its own subject matter, 20 powers of 10 below anything any machine would ever reach, and in exchange it offered a description of a force nobody could measure at the quantum level in the first place. There was no experiment to propose. There was no calculation anyone was waiting for. John Schwartz went on working on it for the next 10 years, mostly with Michael Green, mostly without an audience. Joël Schurk died in 1980, at 33. He did not see any of what followed. 10 years is a long time to hold a position that produces no results anyone else can use. Whatever kept them at it, The thing they were holding onto had a specific shape. Gravity had arrived in their equations without being invited, and it had refused to leave. So, if gravity is compulsory rather than optional in this theory, what else does it refuse to leave out? The result that kept a handful of people working through the late 70s was not that the theory contains gravity. It was that the calculation stops breaking, and the reason it stops breaking comes down to a question that has no answer. A calculation of a collision is a sum. Two things come in, two things go out, and in between the theory has to add up every way the middle could have happened. For point particles, the middle is drawn as lines meeting at junctions, and the junction is a definite place at a definite moment. The infinities from earlier came from that definiteness. The sum runs over ever smaller regions around each junction, and around a mathematical point, there is no smallest region to stop at. Two closed loops arriving and leaving trace out something else entirely. Follow a loop through time, and it sweeps a tube. Two loops merging and separating sweep a single smooth surface, one piece, no corners, no seams, shaped a little like a pair of trousers. Somewhere on that surface, the two tubes became one. The question is where? And the answer is that the surface does not contain the information. Slicing it one way puts the merger early and to the left. Tilting the slices, the way a moving observer in relativity must, puts it later and somewhere else. Both descriptions are of the same surface, and both are correct, because relativity does not permit one slicing to be the true one. No point on that surface is the interaction point. There is nothing to zoom in on, so there is no small region for the sum to run away inside. The tidiness of this shows up in the bookkeeping. In an ordinary field theory, each level of correction brings many distinct diagrams, dozens, and then hundreds of separate arrangements of junctions to be computed and added. In string theory, each level brings exactly one surface. The surfaces are told apart only by how many holes they have. No holes for the simplest process, one hole for the first correction, two for the next, counting upward forever. Each additional hole multiplies the answer by a fixed factor, a number describing how readily a string splits, and that number is the second of the theory's two inputs, which is a shorter list of dials than any framework in physics had ever offered. The standard model of particle physics needs about 19 numbers measured and handed to it before it will say anything, the masses of the quarks and the leptons among them, and it explains none of those numbers. String theory arrived asking for two, a length and a splitting strength, and later work showed that even the second is fixed by the theory's own behavior rather than chosen. A framework with no adjustable dials either predicts our universe or predicts the wrong one. What became of that promise is a story for later tonight. So the whole infinite catalog of ways a thing can happen collapses into a list of surfaces with more and more holes in them. Anyone who has done a serious calculation in the ordinary framework will recognize what a strange gift that is. The hardest part of the work simply is not there. None of that would matter if the answers came out wrong, and the answers do something people rarely describe carefully. It does not merely reproduce Einstein's equations. It reproduces them as the first term of a series. After the familiar curvature term comes another, built from curvature squared and multiplied by the string length squared. Then curvature cubed, multiplied by the string length to the fourth. On and on, each term smaller than the last by the same ratio we met before, the size of the thing being described against the Planck length. General relativity, in this account, is not the theory of gravity. It is the leading approximation to something with more terms in it, and the extra terms are invisible at every distance anyone has ever measured. They would only announce themselves where curvature becomes extreme. The strongest version of all this is easy to state, and took me a while to appreciate properly. Put a string in a curved spacetime and ask whether its own quantum description holds together, the way anyone would check any quantum system for consistency. The check fails in general. Working out the condition under which it succeeds gives an equation the background geometry has to satisfy, and that equation is Einstein's, with the higher corrections attached. The string will not move through a spacetime that disobeys general relativity. It behaves less like an object inside geometry and more like a test the geometry has to pass. Now, the part that honesty requires, because the word finite gets used loosely here. The one-hole surface was shown to give finite answers early on, and the two-hole case followed. Nobody has ever proved that every surface, to every order, gives a finite answer. It is widely believed, and it has not been demonstrated. There is a second thing, sharper than the first. Even granting that every term in the list is finite, the list itself does not add up. The size of the terms grows faster than the extra factors shrink them, roughly as fast as the factorial of the number of holes, so the sum runs away no matter how small the splitting number is made. A series like that can still be useful, and physicists use it, but a sum of finite terms that does not converge is not the same thing as a finished theory. The gap between those two statements is where a great deal of the argument in this subject lives. It also matters that string theory is not the only attempt, and the others are not fringe work. Each one takes the same infinity and gives up something different to get rid of it, and each sacrifice is real. Loop quantum gravity refuses to treat geometry as a stage. Instead of quantizing a field living in spacetime, it quantizes spacetime, and the result is that area and volume stop being continuous. Written out, the area of a surface comes in a sum of terms built from half integers, each multiplied by the Planck length squared, so there is a smallest area that is not zero. Space, in that account, has a grain. What the approach does not do is bring the other forces along. It is a theory of gravity and nothing else, and the particles of the standard model have to be added afterwards by hand. Asymptotic safety, proposed by Steven Weinberg in the 1970s, gives up almost nothing and bets everything on one number. The strengths of forces change with energy, and the suggestion is that gravity's strength stops changing at very high energy, settling at a fixed value. If that happens, the endless list of measured numbers from earlier collapses to a short one, and ordinary field theory survives intact with no extra dimensions and no strings. Calculations using approximate methods keep finding such a fixed point. Whether the approximations can be relied on is exactly what is in dispute. Causal dynamical triangulations gives up the hope of solving anything by hand. Spacetime is built out of small, four-sided pieces glued together. Every arrangement is weighted, and the whole thing is run on a computer. Out of that comes something nobody put in. At large scale, the result behaves as four-dimensional. At very small scale, the dimension measured by watching how a disturbance spreads drops toward 2. The price is that a numerical result is hard to reason about and harder to connect to particles. 4 programs, 4 sacrifices, and not one measurement anywhere that separates them. String theory gave up the number of dimensions in any prospect of a laboratory test. Loop quantum gravity gave up unification. Asymptotic safety gave up the idea that gravity is special. Causal dynamical triangulations gave up the pencil. Anyone choosing between them in the late 70s was choosing on grounds other than evidence, and everyone involved knew it. What string theory had, and the others did not, was a result that arrived without being requested. Gravity had not been sought and could not be removed. The equations of general relativity had emerged from a consistency check on a vibrating loop. The calculation that had defeated every previous attempt stayed finite as far as anyone could push it. A run of results like that changes how people spend their days. It does not amount to evidence, and the people involved were careful in print about the difference. In conversation, and in the choice of what to work on for the next 10 years, the difference held up less well. And the theory still could not describe one of the 4 forces. The weak force has a property that had been measured in 1956, sitting there in the textbooks, and every 10-dimensional theory ran into it. So what is it about the weak force that a 10-dimensional theory cannot swallow? One of the 4 forces treats left and right differently, and that single measured fact came close to ending the whole program. Not because the theory disagreed with the measurement, because any theory that reproduces it stops making sense. The idea being tested has a plane shape. Take any process in nature, write down where everything is, and reverse the sign of every position, so that left becomes right, and up becomes down, and near becomes far. Then ask whether the reversed process also happens. For gravity, it does. For electricity and magnetism, it does. For the force holding a nucleus together, it does. By the middle of the 1950s, this had been checked often enough that nobody thought of it as a question. In 1956, Tsung-Dao Lee and Chen-Ning Yang went looking for where it had been checked for the 4th force, the one responsible for radioactive decay, and found that it had not been. Not once. The assumption had been carried along on the strength of the other 3. Chien-Shiung Wu built the test that year, at Columbia, and the design is easier to picture than most experiments of that era. A small quantity of cobalt-60 was cooled to about 1/100th of a degree above absolute zero, cold enough that a magnetic field could line up the spins of the nuclei so they were all turning the same way. Cobalt-60 decays, and each decay throws out an electron. The only measurement needed was how many electrons came out along the direction the nuclei were spinning, and how many came out against it. If left and right are equivalent, those 2 counts have to match. The reason for that is the entire experiment, and it goes in 3 short steps. A direction of travel reverses in a mirror. A direction of spin does not. A wheel, turning one way, reflected, is still turning the same way in space, while anything moving to the left is now moving to the right. So a difference between along the spin and against the spin is precisely the difference a mirror cannot preserve. The electrons came out preferentially in one direction. Not slightly. Enough that the result was clear within days of the apparatus working. The mirror image of that decay does not occur in nature. Li and Yang were given the Nobel Prize the following year, in 1957, which is close to the fastest that prize has ever moved. Wu, who designed the apparatus and took the measurement, was not included. She spent the rest of a long career being described as the person who had done it. What followed was stranger than a preference. Every particle can be sorted by the relationship between the way it spins and the way it moves, and the two possibilities are called left-handed and right-handed. The weak force does not merely favor one. It attaches to one and ignores the other completely. Written into the equations, the interaction carries a factor that keeps exactly half of each particle and discards the other half, and it always keeps the same half. The cleanest place this shows is the neutrino. Every neutrino that has ever been detected in every experiment arrives spinning in one particular relation to its own motion. The reflected version has never been seen. A neutrino built the other way round would pass through the entire apparatus and through the Earth without registering anything, because the force that would have caught it does not attach to that half. Something similar is true of the hands resting on the covers. They are the same object, reflected, and they do not lie on top of one another. No amount of turning brings the left one onto the right one. Almost everything larger than a molecule can be reflected without consequence, and the difference between the hands is a fact about their shape rather than about the world they are in. Down at the level where the weak force operates, the difference stops being about shape. The universe keeps the two apart on purpose. Which brings the trouble. A theory that treats left and right differently is called chiral, and chiral theories carry a specific illness. Certain symmetries hold perfectly in the equations as written and then fail once quantum effects are included. A quantity that ought to be conserved is not. The failure has a name, and the name is an anomaly. Anomalies are not a matter of precision. When one appears in the symmetry that underlies a force, the theory loses the property that probabilities add up to 1. Some outcome gets a chance of less than nothing, or the chances of all outcomes some past certainty. A theory in that condition does not make a wrong prediction. It makes no prediction because there is nothing left to interpret as a likelihood. A distinction is needed here, because not every anomaly is a disaster. Some belong to symmetries that were only ever approximate, and when those fail, the result is a real measurable effect rather than a contradiction. The neutral pion decays into 2 photons at a rate that plane symmetry arguments forbid, and it decays at very close to the rate an anomaly predicts. That calculation is among the cleanest confirmations in particle physics. The fatal case is the other one. When the broken symmetry is the one a force is built on, there is no effect left to measure, only a theory that has stopped being one. The standard model of particle physics is chiral, and it survives this by the narrowest margin imaginable. The anomaly from each type of particle is proportional to its electric charge, and the total has to come out as 0 for the theory to hold together. The sum runs over one family of matter. 3 colors of up quark, each carrying 2/3. 3 colors of down quark, each carrying -1/3. 1 electron should -1. 1 neutrino at 0. 2, -1, -1, and nothing. The total is 0. That arithmetic is doing more work than it appears to. If quarks carried whole number charges, the sum would not vanish. If there were 2 colors of quark instead of 3, it would not vanish. The peculiar business of quarks having charges in thirds, which is usually presented as an oddity of the bookkeeping, is the reason the Standard Model is a consistent theory rather than a pile of meaningless numbers. The charges of the particles in your body are the values that make probability work. Nobody arranged that. It was noticed afterwards when people worked out what the cancellation required and compared it against charges that had already been measured. The match was exact. Going up to 10 dimensions makes the same problem larger in a way that can be counted. The calculation that produces an anomaly involves a closed loop with particles attached around it, and the number of attachments needed depends on the number of dimensions. In 4 dimensions, the dangerous shape is a triangle with 3. In 10 dimensions, it has 6. More attachments give more independent ways for the cancellation to fail, and every one of them has to come out 0 separately. In 1983, the situation got worse. Luis Alvarez Gaume and Edward Witten showed that gravity has its own version of this, and that a chiral theory in 10 dimensions generally produces gravitational anomalies as well as the ones attached to forces. 2 sets of conditions now had to be satisfied at once, using the same ingredients. Most of the candidate theories failed both. There is something particular about the kind of judgment being handed down here, and it took me a long time to see it as the good news it partly is. A theory can lose in 2 ways. An experiment can contradict it, which requires somebody to build an apparatus, secure funding, wait years, and argue about systematic errors afterwards. Or the theory can fail to make sense, which requires a pencil. The second kind of failure is cheaper to establish and impossible to negotiate with. Nature does not have to be consulted, because a theory whose probabilities do not add to 1 has already excluded itself. For the people working on strings in the early 80s, that was the position. The theory needed to be chiral, because the world is chiral and the weak force had settled the matter in 1956. Chiral theories in 10 dimensions produce anomalies. The anomalies would have to cancel exactly in every channel, gauge and gravitational together, with no adjustable numbers available to help, because the theory had only 2 inputs and neither of them was free to be tuned. The odds against that are not the kind of thing anyone bothers estimating. 2 enormous quantities, computed from completely different parts of the mathematics, would have to be equal to the last digit. There was no reason to expect it. John Schwartz and Michael Green spent a good part of 1984 working out both sides anyway. So what happened when they finished the subtraction? 2 enormous quantities, computed from opposite ends of the mathematics, had to cancel to the last digit, and in the summer of 1984 they did. The result took a few months to compute and changed the field in an afternoon. Understanding what canceled, and why the cancellation was so specific, is the whole of it. The danger was the anomaly from the last part, the flaw that makes a chiral theory in 10 dimensions contradict itself, its probabilities refusing to add to 1. A theory with that flaw is not wrong about an experiment. It is meaningless, a set of equations that no longer describes anything. Every candidate string theory that contained matter, and so had to distinguish left from right, appeared to carry it. An anomaly is not one quantity, but a sum of contributions, one from each kind of particle circulating in a certain quantum process. Some push the total one way, some the other. For most theories, the pushes do not balance, and a leftover remains, and the leftover is the illness. The question Green and Schwartz were asking was whether, For some particular theory, every contribution might cancel against every other, exactly, leaving nothing. There were two sources of anomaly to worry about, and both had to vanish at once. One came from the forces, from the particles that carry the strong, weak, and electromagnetic interactions. The other, found the year before, came from gravity itself, from the gravitons circulating in the same kind of loop. A theory could kill one and keep the other, which was no help, because keeping either is fatal. Both had to reach zero together, using the same ingredients, with no freedom to adjust them separately. What Green and Schwartz found is that the whole anomaly, gauge and gravitational together, sometimes splits apart in a particular way. It factors, the way a number like 15 factors into 3 times 5. The large, complicated expression describing the total anomaly could be written as one factor that depends on the choice of force symmetry, multiplied by a second factor that is the same for every theory. If the first factor can be made to vanish, the entire anomaly vanishes with it, both kinds at once, because they are two parts of one product. There is a piece of how the factoring works that repays a closer look because it is the mechanism itself, not a picture standing in for it. The cancellation is not automatic once the number is right. A leftover remains even for the good symmetry, and it has to be mopped up by a field the theory already carries, one of the higher form fields that later turned out to describe branes. That field shifts in a compensating way whenever the symmetry is applied, and its shift is arranged to eat exactly the leftover anomaly, the way one entry in a ledger can be defined to absorb whatever imbalance the other entries produce. For that trick to work, the leftover has to have precisely the factored form that the good symmetry, and only the good symmetry, provides. The number and the mechanism are locked together. So the impossible-looking demand collapses into a single condition. Find a force symmetry for which that one factor is zero. Not two conditions balanced by luck, but one target, and either a given symmetry hits it or it does not. The factor is built from the particle content of the symmetry, and for almost every choice it comes out non-zero. Green and Schwartz worked through the possibilities. The symmetry structures large enough to be interesting almost all failed. Then they reached one particular group, a specific large symmetry that mathematicians label by its size, and the size is 496. For that group, and essentially that group alone among the plausible candidates, the factor vanished. The number 496 is doing something strange because it arrives twice from unrelated directions. On one side, it is the number that makes the anomaly factor cancel, read off from the structure of the dangerous quantum process. On the other, it is a property of the symmetry group itself, the count of independent directions the symmetry contains, a fact of pure mathematics with no reference to anomalies at all. Two computations that share no steps, one about a physical inconsistency and one about the shape of an abstract group, name the same number. When two roads that were not built together arrive at the same address, people take it as a sign the address is real. That instinct is the one the last part warned about, the one that has been right often and occasionally disastrously wrong. But it is a powerful instinct, and in the autumn of 1984, it ran through theoretical physics like current through a wire. The effect was not gradual. Before the calculation, a few dozen people worldwide worked on string theory, most of them quietly, several of them advised by colleagues to find something more promising. Within a year, the number was in the thousands. Graduate students changed direction, Senior physicists retooled, journals filled. The event acquired a name that tells you how it felt from inside: the first superstring revolution. There is a plainer way to see why one cancelled anomaly moved so many people, and it goes back to what the theory had been promising. The whole appeal was that string theory had almost no freedom, that it could not be adjusted to fit, that it either worked or it did not. A theory you can tune to match anything explains nothing, because it would have matched the opposite result just as well. A theory with no dials, that survives only for one exceptional choice out of countless failures, is doing the opposite. When it fits, the fit means something, because it so easily might not have. That is the honest core of why the cancellation mattered, and it needs separating from what it did not establish. It did not show that string theory describes our world. It showed that the theory is internally consistent for particular choices and self-contradictory for the rest, which is a statement about the theory alone, not about nature. A framework can be perfectly consistent and still describe no universe that exists. Consistency is a gate, not a destination, and passing it is necessary without being nearly sufficient. The distinction is easy to lose, and a great deal of the argument that fills the rest of this story comes from losing it. One camp reads mathematical consistency, especially a consistency as narrow and hard-won as this one, as strong evidence that the structure is pointing at something true. Another camp reads it as exactly what it says and no more, a property of the equations, silent about whether any of it touches the world. Both camps were in the room in 1984, and both were right about something, and the disagreement between them has never closed. What the cancellation did settle was narrower and solid. The anomaly that had seemed to doom every realistic string theory could be evaded, and the ways of evading it were few. Only a small number of symmetry structures passed, which meant the space of possible string theories, moments earlier looking hopeless, suddenly looked almost prescribed. The theory had been rescued by being made more rigid, not less. But the rescue came with a shape that would define the next decade. The condition did not pick out a single theory. It left a short list. The group of size 496 could be realized in more than one way, and other consistent constructions were found alongside it, each avoiding the anomaly by its own route. A theory meant to be unique had passed its hardest test and emerged as several. Within a year, the count settled at 5. 2 of them built the required symmetry from the group of size 496 in 2 different ways. The others reached consistency by routes of their own, with different particles and different structures, each one whole, each one anomaly-free. Nobody could say which, if any, was the world. So the field poured in to work on a theory that had just proved it could exist and inherited 2 problems at once. 5 versions where there was meant to be 1, and 10 dimensions where the world plainly has 4, leaving 6 unaccounted for, folded away somewhere too small to see, in a shape nobody had yet chosen. The theory needs 9 dimensions of space, and we can point to 3, and the 6 that are missing do more than hide. Their shape decides how many kinds of matter exist. That claim sounds extravagant until we follow how it was arrived at, which begins 100 years ago, with somebody adding 1 dimension rather than 6. In 1919, a mathematician in Königsberg named Theodor Kaluza did something with Einstein's equations that nobody had asked for. He wrote them out in 5 dimensions instead of 4. Not to hide a dimension, and not to unify anything at first. He wanted to see what the equations would say. The counting is the part that stops people. In 4 dimensions, the object describing the shape of space-time has 10 independent quantities in it. In 5 dimensions, it has 15. 10 of those 15 reassemble into ordinary 4-dimensional gravity, exactly as Einstein wrote it. 4 of the remaining 5 assemble into a single object with 4 components. That object obeys Maxwell's equations. Electricity and magnetism come out of 5-dimensional gravity, unrequested, and one quantity is left over with nowhere to go. Kaluza sent the paper to Einstein, who held it for about 2 years and then helped him publish it in 1921. Einstein wrote to him that the idea of doing it through a 5-dimensional world had never occurred to him. The enthusiasm was real, and it did not last. The reason it did not last is the same objection anyone would raise. A 5th dimension of space is not a subtle thing to have missed. The answer came in 1926 from Oskar Klein, a Swedish physicist, and it is the piece the whole subject still runs on. The extra dimension is closed. Instead of running off to infinity like the 3 we move in, it comes back to where it started, and the loop it makes is small enough that nothing we have ever done has probed across it. What Klein noticed next is better than the hiding. Anything traveling around a closed loop can only carry certain amounts of momentum in whole number multiples set by the size of the loop, because the wave describing it has to fit around and meet itself. A wave that does not close on itself does not exist. Written out, the momentum around the loop equals a whole number times Planck's constant divided by the radius. Seen from our 4 dimensions, that whole number appears as electric charge. So electric charge comes in discrete units because a wave has to fit around a circle. Nobody had explained why charge is quantized before, and the explanation arrived as a side effect of geometry. Klein worked backwards from the size of the electron's charge to the size of the loop, and got something near 10 to the minus 30 of a centimeter. There was a bill attached. If the momentum around the loop comes in whole number steps, then every particle should have heavier copies of itself, one for each step, with masses climbing in multiples of Planck's constant divided by the radius times the speed of light. A ladder of them, reaching upward forever. None has ever been seen, which puts a floor under how small the loop has to be, and the smaller the loop, the heavier the first rung and the further out of reach. And the leftover quantity, the 15th one, never went away. It describes the size of the loop, and nothing in the equations fixes what that size should be. A quantity with no equation telling it where to sit is free to drift, and if the loop drifts, then the strength of electromagnetism drifts along with it, since the 2 are one number seen from 2 directions. Nobody in the 20s had a way to hold it still. The same difficulty, multiplied many times over, is waiting for us later tonight. Kaluza and Klein's work sat mostly unused for 50 years. Einstein moved on to the problem he spent the rest of his life on, and did not take the extra dimension with him. There is something I have never fully resolved about that. The tool he set down in 1926 is the direct ancestor of the only version of this idea that anybody is currently able to test, and the test is being attempted this decade. He had it in his hands and let it go, for reasons that were sensible at the time. 10 dimensions makes the same move 6 times over, and the arithmetic of possibilities changes completely. 1 dimension can be closed in exactly one way. A loop is a loop. 6 dimensions closed together can be joined in an enormous number of shapes, differing not in size but in how they are connected, in how many independent ways there are to travel through them and come back. Some of the shapes have handles. Some have passages through them. Nothing in the 10-dimensional equations says which one to use. 2 requirements narrow the field, and both are strict. The 10-dimensional equations have to be satisfied with nothing sitting in the extra dimensions, so the compact shape has to carry no curvature of the kind that Einstein's equations respond to. It must curve without curving in that particular sense, which sounds impossible and is not. And a fragment of supersymmetry has to survive the folding, because supersymmetry is what removed the state with negative mass squared, and losing it brings that state back. Shapes meeting both conditions were not invented by physicists. Eugenio Calabi conjectured in the 1950s that they exist, as a question in pure geometry with no physics attached. Xing-Tung Yao proved it in the late 70s and received the Fields Medal for that and related work in 1982, at a point when he held no passport of any country. In 1985, Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten showed that these are the shapes string theory requires. And now the part that makes the whole exercise more than tidy. The physics appearing in our 4 dimensions does not depend on how large the folded shape is, and it does not depend on where it sits. It depends on how the shape is connected, on the number of independent holes running through it, counted separately for holes of each kind, 1-dimensional loops and 2-dimensional surfaces, and so on upward. Those counts get combined into one number. Add up the holes of each kind, alternating the sign as the dimension goes up, and the total is called the Euler characteristic of the shape. It has been a standard quantity in geometry for a century and a half. For a donut, it is 0. For a sphere, it is 2. For the 6-dimensional shapes in question, it can be a great many values. For these particular shapes, the number takes a tidier form as well. It comes out as twice the difference between 2 of the whole counts, so an Euler characteristic of 6 requires those 2 counts to differ by exactly 3. The result that came out of the 1985 work is one line. The number of families of matter appearing in 4 dimensions equals half the size of that number, ignoring its sign. 3 families requires an Euler characteristic of plus or minus 6. It is difficult to describe how odd that is without overstating it, so the plainest version will do. Matter arrives in 3 families and always has. The electron, the muon, the tau, the up and down quarks, then charm and strange, then top and bottom. Everything in a body is built from the first family, and the other 2 show up in accelerators and in cosmic rays and then decay. Nobody has ever explained why there are 3. Not 2, not 7. The standard model takes the number as given and proceeds. Here the number stops being given. It becomes a whole count in a shape 6 dimensions wide and smaller than anything, whose size and position make no difference at all to what we observe. Only its connectivity reaches us. Whether that counts as an explanation is a fair question, and the honest answer has 2 halves. One unexplained number has been replaced by a question about which shape, and if something picks the shape, then a great deal has been gained. If nothing picks it, then the 3 families have been traded for a choice, and a choice is not a reason. By 1985, nobody knew which of those was the case. Hundreds of thousands of suitable shapes have since been constructed, and it remains unproven whether the number of them is even finite. What the folding did preserve was that fragment of supersymmetry, kept alive on purpose, surviving all the way down into 4 dimensions. Out of everything in this story, that fragment is the one thing that predicted particles at an energy a machine could reach. So what exactly was it promising, and what would it take to find? The surviving fragment of supersymmetry made one promise that a machine could keep or break, and for 30 years it was the most testable thing string theory had. The promise was a set of particles nobody had ever seen, at an energy we were about to reach. It grew out of a problem that has nothing to do with strings, and everything to do with why anything has the mass it has. The problem starts with the Higgs. The Higgs is the field that gives the other particles their mass, and like any quantum field, it has a mass of its own. The trouble is that its mass does not sit still. Every other field it touches reaches in and shifts it, through the constant flicker of particles appearing and vanishing that quantum mechanics never turns off. Each of those contributions is not small. Written out, the correction to the Higgs mass squared is proportional to the square of the highest energy at which the theory still holds. If the theory holds all the way up to the Planck energy, that correction is the Planck energy squared. The measured Higgs mass sits near the energy scale of the weak force, and the Planck scale is 1,000 trillion times higher. Squaring that gap turns 1,000 trillion into something with 30 zeros. So the raw contributions to the Higgs mass squared are larger than the answer we measure by roughly 30 powers of 10. The only way to end up with the small number we measure is for those enormous contributions to cancel. Each one is set by constants of nature, fixed and unrelated, computed from different particles. For them to add up to almost nothing, they have to agree with each other digit after digit, roughly 30 digits deep, and there is no reason in the theory for them to. Adjust any one of them in the 30th decimal place, and the Higgs mass leaps to the Planck scale, taking the structure of matter with it. Physicists find that kind of coincidence difficult to accept, and the reason is not aesthetic. A number that has to be tuned to 30 places to keep the world standing is usually a sign that something is holding it there, some mechanism not yet in the equations. The alternative is that the universe balanced a pencil on its point at the beginning, and it has not fallen in 14 billion years. Supersymmetry offers the mechanism, and it does it without anyone tuning anything. Every particle contributing to the Higgs mass has a superpartner, and a partner of the opposite type, a boson paired with a fermion. Those two types contribute with opposite signs. A fermion pushes the Higgs mass one way, its boson partner pulls it the other way by the same amount, and the two nearly erase each other. The cancellation is not arranged by hand. It follows from the pairing, the same pairing that had entered the string story a decade earlier to remove the state with negative mass squared. The erasure is only perfect if the partners have equal mass. They do not, because we would have seen them. So the cancellation is close but not exact, and what is left over is set by how far apart in mass the partners sit. For the leftover to match the Higgs mass we measure, the superpartners have to weigh in somewhere near the energy scale of the weak force, a few hundred times the mass of a proton, up to perhaps 1,000. The logic runs one way only, and that matters later. Light superpartners keep the Higgs mass natural. Heavy superpartners do not, because the further apart the partners sit, the more of that 30-digit coincidence comes creeping back. The theory does not merely allow the new particles to be nearby. It needs them nearby, or its reason for existing weakens. That is a definite range, and it is the range a large enough collider can search. There was a second thing pointing at the same window, and it arrived from a different direction entirely. The three forces described by the standard model, the strong, the weak, and the electromagnetic, each have a strength, and those strengths change with energy. The strong force weakens as the energy rises, the way we saw quarks come loose inside a proton. The other two behave differently, one strengthening, one drifting. Their strengths are not constants but slide, slowly, in proportion to the logarithm of the energy. Follow the three of them upward, and something almost happens. In the standard model as it stands, the three lines that track the three strengths climb toward each other and nearly meet at an energy near 10 to the 16th times, the mass of a proton, close to the Planck scale but a little below it. Nearly meet and miss. Three lines that pass through very nearly one point, but not quite one point. Now add the superpartners to the theory. Their presence changes how fast each of the three strengths drifts, because the drift depends on which particles exist to take part. With the superpartners included at roughly the weak scale, the three lines bend slightly, and the near miss closes. They cross at a single point, within the accuracy anyone can compute. Three separate measurements, made at low energy in three different kinds of experiment, extrapolated across 14 powers of 10, arrive together. That convergence is one of the reasons a generation of physicists took supersymmetry as close to established before it had been seen once. It could be a coincidence. Three lines have to end up somewhere, and three lines passing through one point is not the same as a photograph of a new particle. But it was the kind of result that felt like a message, and it pointed at the same energy the Higgs argument had pointed at, and both of them sat inside the reach of the machine being built at the time. The place where the confidence really gathered is easy to point to. Two completely independent problems, the stability of the Higgs mass and the meeting of the three forces, asked for superpartners in the same place. Neither problem had anything to do with the other, and neither was invented to support supersymmetry. When two unrelated questions point to the same answer, the answer stops looking like a guess. That is a sound instinct, and it has been right many times in the history of physics. It has occasionally been wrong, and the difference between the two cases is never visible from inside. Grand unified theories deepen the same picture and predate the string version of it. In 1974, Howard Georgi and Sheldon Glashow proposed that the three forces are not merely meeting at that high energy but merging, becoming a single force above it, in the same way electricity and magnetism are two faces of one thing. Their scheme placed quarks and leptons into the same family, which meant the two could turn into one another, which meant the proton, made of quarks, could decay. That prediction is the thread we will pick up shortly, because it is the one grand unification is remembered for, and the reason is that somebody went and looked. For now the point is narrower. The supersymmetric version of these unified theories sharpened every number, and the sharpened numbers all lived in the same neighborhood, a few hundred to a few thousand times the proton mass, exactly where the next machine would reach. So the position at the end of the 1980s was better than string theory had any right to expect. The framework required supersymmetry to hold together at all, and supersymmetry, quite separately, solved the worst fine-tuning problem in particle physics and made three unrelated measurements converge. The particles it called for sat at an energy the Large Hadron Collider was being designed to explore. For the first time in the whole story, a theory built at the Planck scale had handed down a prediction that a machine on Earth could check within a working lifetime. Before that machine could be pointed at the question, another prediction of unification reached its own day of judgment first, in a tank of water beneath a mountain, and the way it ended is the sharpest thing that has happened to any of these ideas. A theory can be beautiful, unifying, and wrong, and we know that because one of them named a number and the number was checked. The theory was the first grand unification. The number was how long a proton lives. Everything string theory has ever been accused of, this earlier idea escaped by doing the one thing that settles anything. The proton is the reason there is chemistry. It sits at the center of every atom, and as far as anyone had ever measured, it lasts. Nothing in ordinary physics lets it decay, because the decay would have to turn quarks into something lighter, and a rule that had held in every experiment forbids exactly that. The number of quarks in the world, counted a certain way, never changes. That rule is not a law anyone wrote down from a principle. It was read off the world, the way the stability of the proton itself was, by noticing that the books always balanced. Rules of that kind have a habit of turning out to be approximate. They hold until a force is found that breaks them, and then they become an accounting convenience rather than a law. The grand unified theory of Howard Georgi and Sheldon Glashow, written down in 1974, broke it on purpose. Their proposal put quarks and the electron into a single family, governed by one force above the unification energy. Members of a family can turn into one another. That is what being in a family means in this part of physics. If a quark and an electron sit in the same family, then a process exists, however rare, that turns one into the other. Rare, because of the energy. The transition runs through a very heavy carrier particle, one that weighs about 10 to the 16th times the mass of a proton, the same scale where the three forces nearly met in the last part. A force carried by something that heavy has an almost unimaginably short reach, and processes it mediates are throttled down by the square of that mass sitting in the denominator. The consequence is a proton that decays, but slowly. The predicted lifetime lands around 10 to the 31 years. That number is hard to feel, so it helps to place it against the age of the universe, which is about 10 to the 10 years. The proton's predicted life is not a little longer than the universe. It is 100 billion times longer. Which sounds untestable, and the turn that follows is what makes the whole thing work. A single proton lasting 10 to the 31 years cannot be watched. But a lifetime is a statement about probability per unit time, and probability adds. Gather 10 to the 33 protons into one place, more than the number in a swimming pool, and if each has a tiny chance of decaying this year, then a handful of them should decay this year, in that pool, where you can stand and watch. So the way to test a number 100 billion times the age of the universe is to stop watching one proton for an eternity and start watching an eternity of protons for a year. The same total, cut the other way. A thing too slow to see becomes a thing that happens on a Tuesday if you bring enough of it into one room. They built the room. In the early 1980s, in a mine in Ohio and in a zinc mine under a mountain in Japan, Physicists filled enormous tanks with ultra-pure water and lined the walls with light detectors. Water is mostly protons, in the nucleus of every hydrogen atom in every molecule. A tank holding thousands of tons of it holds more protons than there are stars in every galaxy we can see, many times over. The signature they watched for was specific. Georgi and Glashow's theory did not merely say the proton decays. It said how. The favored channel turned a proton into a particle called a neutral pion and a positron, the antimatter twin of the electron. Both of those carry energy away in a distinct pattern, and in water traveling faster than light travels in water, which produces a faint cone of blue light the detectors are built to catch. The theory even told them roughly how often. With that much water, the tanks should have recorded a few of those blue cones a year, if the lifetime was what the theory said. The experiment was not a fishing trip. It was a specific prediction with a specific rate, and the apparatus was sensitive enough to see it. Nothing came. Not the first year, not the next. Year after year, the tanks watched their vast stock of protons and recorded no decay of the kind the theory required. Each empty year pushed the lifetime longer, because a proton that has not decayed in all that watching must live at least long enough to explain the silence. By the late 80s, the measured floor had climbed above the ceiling the theory had predicted. The minimal Georgi-Glashow model said the proton should live no longer than about 10 to the 31 or 32 years. The experiments had shown it lives longer than that. The two numbers had crossed, and when the floor of the measurement rises above the roof of the prediction is finished. The detector in Japan, enlarged and rebuilt into what is now called Super Kamiokande, has since pushed the proton's lifetime past 10 to the 34 years, in the channel the theory cared about most. That is 3 orders of magnitude beyond where the simplest unification lived. The theory that had merged 3 forces, placed matter into elegant families, and helped inspire an entire generation, made one falsifiable prediction, and the prediction failed. What died here and what survived are 2 different things. The idea of grand unification is not gone. More elaborate versions, many of them supersymmetric, push the proton's lifetime higher and survive, for now. What died was the specific, minimal, beautiful theory, the one clean enough to be cornered. It was killed by counting the absence of an event, which is the least dramatic and most final kind of evidence there is. That is the standard against which everything in this story should be set, and it is why this part exists at all. Georgi and Glashow's theory was elegant, and it unified, and it was mathematically consistent. Every quality string theory is praised for. None of those qualities saved it. It made a number. Somebody built a tank of water. The number was wrong, and that was the end. The elegance did not get a vote. Hold that beside string theory, and the contrast is uncomfortable in a particular direction. The minimal unified theory was killed because it was falsifiable, because it said the proton must decay by a certain age and let itself be checked. String theory has never yet named a number in that way, never told the world a specific thing that must appear at a specific scale and staked itself on the answer. That has been read as a strength, a theory too deep to be cornered, and it has been read as the deepest possible weakness. Both readings are alive, and this part is where the disagreement gets its teeth. There is a coda that carries the story forward, because the tanks are still watching. A far larger detector, Hyper-Kamiokande, is under construction and expected to begin operating in the coming years. It will hold on the order of 250,000 tons of water, and its reach into the proton's lifetime will extend well past what any experiment has managed. Many supersymmetric, grand unified theories predict decay just beyond the current limits. Inside the window, the new detector will open. So, a prediction that grew, in part, out of the same supersymmetry string theory needs is about to be tested again, more sharply than ever. The proton will either begin to come apart in that water, on camera, or it will go on refusing and push another family of theories over the edge the first one went over. Before that verdict arrives, the theory itself was about to fracture in a way that had nothing to do with any experiment, into not one version but 5. By the late 1980s, there were 5 consistent string theories, and a theory of everything is not supposed to come in 5. Each was complete. Each contained gravity, avoided the anomalies, lived in 10 dimensions. 5 different answers to a question that was only supposed to have 1, and no reason inside any of them to prefer it over the other 4. Their names matter less than the ways they differed. One built from open strings and closed ones together. 2 built only from closed loops, differing in whether the 2 waves running around a loop were treated the same way or as mirror images. 2 more of a hybrid kind, carrying 2 different large symmetry structures, one of them the very group whose size had made the anomaly cancel a few years earlier. Different particle contents, different symmetries, all consistent. For a framework whose entire appeal was that it had almost no choices in it, this was close to an embarrassment. The whole argument for taking string theory seriously had been that it asked for 2 numbers and left nothing else free. Now it turned out there were 5 doors, and the theory that was meant to have no dials had at least a 5-way switch on the front of it. The resolution began with a shift in how a theory can be looked at, and the simplest way in is a fact about a single closed dimension. Take one of the extra dimensions and roll it into a loop of radius r. A string in that space can do 2 separate things. It can orbit around the loop, carrying momentum, and we saw in the Kaluza-Klein story that this momentum comes in whole number steps, in units of 1 over r. The larger the loop, the smaller and more closely spaced those steps. But a string can do something a point particle cannot. It can wrap around the loop, like a rubber band stretched over a rolled poster, and once wrapped, it cannot slip off, because it is a closed loop caught around another closed loop. A wrapped string carries energy from being stretched, and that energy is proportional to how far around it has to reach, which is proportional to r itself. The larger the loop, the more energy each wrapping costs. So the string has 2 ledgers. One, the orbiting, costs less as the loop grows. The other, the wrapping, costs more as the loop grows. One falls as 1 over r, the other rises as r. Set them side by side and something happens that should not quite work. Write down the full list of energies the string can have, and it is symmetric. Swap the 2 ledgers, the orbiting numbers for the wrapping numbers, and at the same time replace the radius r with its inverse, 1 over r, and the entire list of energies comes back identical. Not similar. The same list, particle for particle, energy for energy. So, a string moving in a universe where that dimension is enormous is doing something no measurement can tell, apart from a string in a universe where the same dimension is tiny. There is no measurement from inside that separates a loop of radius r from a loop of radius 1 over r. The two are not similar situations. They are the same physics wearing two descriptions. This is called T-duality, worked out in the mid-80s, and it does something quietly radical to the idea of size. Below a certain radius, there is nothing new to find, because going smaller is the same as going larger again, reflected. There is a shortest distance that means anything, and it sits where r equals 1 over r, where the loop is its own inverse. Shrink past that point, and you are not entering a smaller world. You are walking back out into a large one. The first thing this did was collapse the 5 theories toward each other. 2 of the 5, when one of their dimensions was curled up, turned out to be T-dual. Roll a dimension of the first down small, and it becomes the second, with that dimension rolled up large, the whole spectrum matching. They had never been 2 theories. They were one theory, seen from the 2 ends of a single dimension. The same held for another pair. 5 began to look like 3. A second kind of duality did something bolder, and it reached the part of physics that had always been hardest. Every calculation so far in this story worked only when interactions were weak, when strings split and joined rarely, because the whole method was that list of surfaces with more and more holes, each hole multiplied by the small splitting number. If that number is small, later terms are tiny and can be dropped. If it is large, every term matters, the list is useless, and nobody can compute anything. Strongly interacting theories had been a wall for 50 years, in every part of physics, not only this one. Strong-weak duality proposed that some theories, when their interactions grow so strong that no calculation is possible, become identical to a different theory whose interactions are weak, where calculation is easy. The strength of interaction in one is 1 over the strength in the other. Turn the coupling up in the first theory past the point of hopelessness, and you are looking at the second theory with its coupling turned comfortably down. Something similar had first been glimpsed for a simpler case, and around 1990, Ana Maria Font, Luis Ibáñez, Dieter Lust, and Fernando Quevedo were among those who brought this kind of strong-weak relation into string theory itself. When it was applied across the remaining theories, another wall between 2 of them dissolved. The one that was hopeless to compute at strong coupling was the one that was easy at weak coupling, described the other way around. By 1994, the 5 theories were laced together by these relations, and it no longer made sense to count them as 5. They were regions, connected by dualities, of something none of them was individually. The picture in people's minds began to change from 5 separate lands to 5 provinces of one country whose interior had not yet been mapped. Edward Witten drew that map in a lecture in the spring of 1995 and added a room nobody had counted. Push one of the string theories to strong coupling, he showed, and a new dimension opens up. The theory that looked 10-dimensional grows an 11th dimension as its interactions strengthen, a dimension whose size is fixed by the coupling itself, invisible when the coupling is weak and unfolding as it grows. At full strength, the theory is not a theory of strings in 10 dimensions at all. It is something living in 11. That 11-dimensional thing was not new either, and the fact that it turned up here is one of the stranger returns in the subject. In 1978, Eugene Kremer, Bernard Julia, and Joël Schurk had written down a theory of gravity in 11 dimensions, the highest number in which such a theory can be built consistently. It had been set aside because it was not a string theory, and nobody could make it yield the real world. Now it reappeared as one more province, the strong coupling face of a theory people thought they understood. Just before Witten's lecture, Christopher Hull and Paul Townsend had published a paper arguing that the string dualities pointed toward exactly this kind of underlying unity. Witten's contribution was not to invent the idea alone. It was to show, with enough force and detail that the field turned overnight, that the 5 theories and the 11-dimensional one were 6 views of a single structure. He gave the structure a letter. He called it M theory, and declined to say what the M stood for, suggesting magic or mystery, and much later allowing that he had been thinking of membrane. The name is doing something honest, whether or not it was meant to. The 6 known corners are described. The thing they are corners of has never been written down. That last sentence is the one to sit inside, because the popular account skips it. M theory is not a set of equations somebody solved. It is the name for whatever object has these 6 things as its limits, defined by its edges rather than its interior, known the way a country's shape is known from its coastline, before anyone has walked the middle. The dualities that connect the corners are checked and solid. The master equations that would govern the whole are not written, and after 30 years they are still not written. In the search for what filled the middle, physicists found that the theory of strings contained objects that were not strings at all and had been hiding in a piece of it everyone thought they understood. For 25 years, the theory was named after strings, and then somebody noticed that the strings had ends, and asked the question nobody had asked. Where do the ends stop? The answer turned out to be an object more important than the string. An open string is a length with 2 loose ends, and the equations governing it cannot be written without saying something about what happens at those ends. The mathematics offers 2 ways to close the books. Either the end is free, able to move however it likes, or the end is fixed, pinned to a definite location. For a long time, everyone chose free, without much discussion, because a fixed end seemed to break one of the rules the theory was built to respect. A pinned end singles out a place. It says this spot is different from that spot. This is where an end must lie, and that is where it may not. And a theory that began by making all locations equivalent is not supposed to allow that. The condition looked like a violation of the very symmetry that made the whole framework consistent. So the fixed choice sat in the textbooks as a mathematical possibility that physics did not use. The way out turns an apparent contradiction into a new object, and it goes in 3 steps. If the end of a string is pinned to a location, then the location itself must be a thing. Not empty space with one point arbitrarily marked, but a physical surface sitting in the space, a surface that strings are required to end on. The symmetry is not broken after all. It is respected by allowing the surface to be an object in its own right, able to move, able to be placed anywhere, so that no location was singled out in advance. These surfaces are called D-branes, and the letter records that fixed boundary condition. A brane can have any number of dimensions the space allows. A point-like one, a line-like one, a sheet, a volume, on upward. Open strings live with both ends resting on them, sliding freely within the surface while staying attached to it, the way a raindrop can run along a window pane without leaving the glass. Joseph Polchinski had been aware of these fixed-end solutions for years, as had others, filed under mathematical curiosities. In 1995, Months after Witten redrew the map, Polchinski worked out what they really were, and the result changed the size of the whole subject. The branes were not bookkeeping. They were dynamical objects, with mass, with charge, obeying equations of motion, bending the space around them exactly as any massive charged thing does. Reading his own account later, the thing that comes through is not triumph but a kind of vertigo. He wrote of the moment of realizing that the world was not as he had thought it was, of a discovery that reorganized what the theory even contained. The framework called string theory had, sitting inside it the whole time, a population of higher dimensional objects that nobody had counted as part of the furniture. What makes a brane physical rather than decorative is that it carries charge, and the charge is the same kind of thing that makes the graviton compulsory. Recall that a massless spin-2 particle must couple to energy, universally, which is what forced gravity into the theory. Higher forms of that same logic exist. There are fields in string theory that couple not to points but to extended objects, a field that a one-dimensional object can carry charge under, another that a two-dimensional sheet can carry charge under, and so on. For each such field, the object that carries its charge is a brane of the matching dimension. The branes are not optional guests. They are demanded by the fields the theory already contained. Their mass has a particular character that matters for everything after. Written out, the mass of a brane per unit of its volume is proportional to 1 over the string coupling, the same small number that measured how rarely strings split. When interactions are weak and that number is small, 1 over it is large, and the branes are enormously heavy, far too heavy to make in any collision, which is why they stayed invisible in every earlier calculation. They were always there in the equations. They were simply too massive to appear in the weak coupling world where all the work had been done. That mass formula does something else, and it is the reason branes reorganize the field. A string's own mass does not depend on the coupling at all. A brane's mass runs as 1 over the coupling. So as the interactions in a theory grow stronger, the coupling rising toward 1 and beyond, the branes get lighter, while the strings stay where they are. Push far enough and a brane can become lighter than a string. The thing you had been treating as the fundamental object, the string, is no longer the lightest thing in the theory, and something you had dismissed as impossibly heavy is now the natural thing to build from. Which unpicks the word fundamental in a way the subject is still absorbing. In one description, the string is basic and the brane is a heavy composite. Cross a duality to the strongly coupled side, and the brane is light and behaves like the basic object, while the string looks like something wrapped up out of it. Neither description is the true one. Which object counts as elementary depends on which corner of the map you are standing in, and the map has no privileged corner. This is what the 11-dimensional room was really about. When one string theory grew its extra dimension at strong coupling, what unfolded were branes. A two-dimensional membrane in 11 dimensions, wrapped tightly around the new small dimension, looks from a distance like a one-dimensional string in 10. Leave it unwrapped, stretched out flat, and it is a membrane, a thing with area, a sheet. The string had never been more than one appearance of a membrane seen edge-on. The membranes come in a small number of basic kinds in 11 dimensions, and every string and every brane in every one of the 10-dimensional corners is one of them, wrapped or unwrapped, seen from one angle or another. The proliferation of objects that had seemed to clutter the theory resolved into a very short list, viewed through the dualities. Underneath 5 string theories and 11-dimensional gravity sat a handful of membranes, and the whole zoo was those few objects wearing different clothes in different provinces. There is a plainer way to feel what happened here, and it took me time to state it without exaggerating. A theory that had been named, taught, and argued over for a quarter of a century as a theory of one-dimensional strings turned out not to be primarily about strings. The strings were one case of a wider family, and not always the important case. The name had frozen an early impression into a label, and the label had outlived its own accuracy, the way names often do. And the branes did something the strings alone had never managed. Stack several of them together, flat, one on top of another, and the open strings stretched between them behave in a specific way. A string with one end on one brane and the other end on a neighbor carries the charge of both. The pattern of all such strings, running between all the branes in a stack, reproduces exactly the kind of force field that describes the strong and weak and electromagnetic interactions, with the number of branes in the stack setting the size of the symmetry. So the forces of the standard model, or structures very much like them, could be made to live on a stack of branes, while gravity moved in the full space around them. Matter and its forces painted onto a surface, gravity filling the room the surface sits in. That division would become the seed of the strangest result in the whole story. Because once you can stack branes and pile mass and charge into one region, you can ask what happens when you stack enough of them in a small enough space, and the answer is that you have built a black hole out of pieces you understand. The hardest number string theory has ever produced is a count of the inside of a black hole, and it came out right to the last factor in a calculation anyone can check. This is the closest the theory has come to touching the ground. It is also where its limits show most sharply, because the black hole it counted is not one that exists in the sky. The problem it solved was 20 years old and had nothing to do with strings. In the early 1970s, Jacob Bekenstein and Stephen Hawking found that a black hole has a temperature and an entropy, which no one had expected a region of pure gravity to have. A black hole is not supposed to be warm. It is supposed to be a hole. Entropy is the piece that matters here, and the word means something plainer than it sounds. The entropy of a thing counts how many distinct arrangements of its hidden parts would look identical from outside. A tidy room has low entropy, because few arrangements of its contents count as tidy. A messy room has high entropy, because an enormous number of different arrangements all count as messy. Entropy is a count of the ways the inside can differ while the outside stays the same. Bekenstein and Hawking gave the black hole a definite entropy, and the formula is one of the strangest in physics. The entropy is the area of the horizon, divided by 4, measured in units of the Planck area. The Planck length squared. Every other entropy in nature grows with volume, with how much stuff there is inside. This one grows with the surface. A black hole twice as wide across has 4 times the entropy, because area goes as the square of size, not 8 times as a volume would. An entropy is a count of arrangements, and that raises a question with a sharp edge. Arrangements of what? Every entropy anyone had ever computed was a count of the microscopic pieces of a thing, the positions and motions of its atoms. The black hole formula gave a number, an enormous number, but general relativity described the black hole with only 3 quantities: its mass, its charge, and its spin. 3 numbers cannot be arranged in 10 to the enormous ways. The relativity picture had no pieces to count. For 20 years, the formula sat there, exact and unexplained. It said a black hole the size of a coin has more possible internal states than there are atoms in the observable universe, many times over, and it did not say what those states were. Something inside a black hole was doing an astronomical amount of hidden arranging, and gravity alone could not name a single one of the arrangements. The pieces were what string theory had just found. In 1996, Andrew Strominger and Kamran Vafa took the branes from the last part and did something a physicist would call building a black hole and a bookkeeper would recognize as an inventory. They chose a particular kind of black hole, a very specific one, and assembled it out of a definite number of branes of definite kinds, wrapped around the hidden dimensions in a definite pattern. The specific kind matters, and honesty requires naming the price. Their black hole was supersymmetric, balanced exactly at the point where its charge equals its mass in natural units, a knife-edge case called extremal. Real black holes in the sky are not like this. They spin. They carry almost no charge. They sit far from that balance point. The reason for the choice was not realism. It was that supersymmetry holds a certain count fixed as the coupling changes, which is the only reason the calculation can be trusted at all. The maneuver the whole result turns on is a simple one, and it is the reason any of this can be trusted. A brane's mass runs as 1 over the coupling from the last part. Turn the coupling down low, and the branes become light, and their gravity becomes feeble, so feeble that no horizon forms. At that setting there is no black hole, only a collection of branes and the open strings stretched between them, sitting in nearly flat space, a quantum system plain enough to count. So they counted it. They counted the number of distinct quantum states that collection of branes and strings could occupy at fixed total charge, using ordinary quantum mechanics with no gravity involved. Then they turned the coupling back up. As it rises, the branes grow heavy, their gravity strengthens, and at strong enough coupling the whole assembly collapses behind a horizon and becomes, unmistakably, a black hole with the entropy Bekenstein and Hawking had written down. The count of states cannot change as the coupling turns because supersymmetry protects it. Whatever number they found in the weak, countable, gravity-free description has to be the same number in the strong, gravitational, black hole description. So they set the two side by side. On one side, the number of brane and string arrangements computed by counting a problem in combinatorics with a definite answer. On the other side, the area of the horizon divided by 4 computed from geometry, a problem in gravity with a definite answer. The two calculations share no methods. One is a tally of quantum states, the other is the size of a surface. They matched. Not approximately, not up to some unknown factor that could be fudged into place. The brane count reproduced the area over 4 exactly, including the 4, including every numerical coefficient that a looser argument would have left dangling. The hidden arrangements the entropy had been counting for 20 years were arrangements of branes and strings, and string theory could list them, and there were precisely as many as the horizon's area demanded. What this proves, and what it does not, are two separate things, and both deserve stating. A number that had been a pure mystery of gravity, unexplained since 1972, was derived from the microscopic pieces of a specific quantum system with no free parameters left to adjust. Loop quantum gravity can also reproduce the area law. but it has to fix one free number by hand to get the coefficient right. The brane calculation fixes nothing by hand. The factor of 4 falls out on its own. What it does not do is describe a black hole you could point a telescope at. The extremal, supersymmetric object is a mathematical cousin of the real thing, chosen precisely because it holds still while the coupling is turned. Later work reached black holes slightly away from that balance point, near extremal ones, and the match held there too, which made the result harder to dismiss as a coincidence of the special case. But the black holes at the centers of galaxies, spinning, uncharged, enormous, remain outside what this method can count. The proof of principle is real. The reach of it is narrow. Even so, something had shifted, and it is the thing that carries into the last stretch of this story. The entropy of a black hole lives on its horizon, on a surface, and counts the states of what is inside. The information about a three-dimensional interior is written on a two-dimensional boundary, in exactly the amount that boundary can hold, 1 bit for every 4 Planck areas. That is a strange place for the inside of a thing to keep its accounts. A volume's supply of possibility, recorded on the wall around it. Nobody had gone looking for that. It came out of a calculation aimed at a different target. The way the graviton had come out of a theory aimed at the nucleus, the way electromagnetism had come out of 5-dimensional gravity aimed at nothing in particular. A pattern runs through this whole history, and it is not the pattern of a theory being confirmed. It is the pattern of a theory being right about things it was not built to address, while staying silent about the thing it was built for. If the surface around a black hole holds every bit of what the inside contains, then a question forms that is larger than black holes. Maybe the surface is not keeping a copy of the inside. Maybe the surface is the whole account, and the inside, with all its depth and all its gravity, is what that account looks like read from a certain angle. Someone was about to make that suspicion exact, and the universe it turned out to describe with perfect precision was not the one we live in. The most successful thing string theory has ever produced describes a universe with the wrong shape, and it describes it perfectly. The paper that started it is the most cited in the field's history. Its central claim has passed thousands of independent checks. And the space it is a claim about curves the opposite way from the space around you. The setup came straight out of the last part. Take a stack of branes, the three-dimensional kind, and pile many of them in one place. Each carries mass and charge, and mass and charge bend the space they sit in. Stack enough, and the bending becomes severe, and near the stack, the geometry settles into a particular shape that has a name, anti-de Sitter space. That shape is where everything turns, so it is the thing to picture first. Ordinary space, the space of a quiet room, is flat, in the sense that parallel lines stay parallel, and the angles of a triangle add to 180 degrees. Anti-de Sitter space is curved, and curved in the direction that pulls inward. A triangle drawn in it has angles that add to less than 180. Light thrown outward slows, turns, and falls back, as though the far edge of the space were a wall that returns everything sent toward it. Space of that kind behaves like the inside of a bowl that has no bottom and no rim, holding its contents near the middle. Juan Maldacena, in 1997, looked at the stack of branes 2 ways at once, and the 2 ways did not agree about how many dimensions there were. From far away, the branes bend space, And what you see is gravity in that bowl-shaped anti-de Sitter geometry, in a certain number of dimensions. Up close, the branes are surfaces with open strings living on them, and what you see is a quantum field theory of those strings, a theory of particles and forces with no gravity in it at all, living on the flat sheet the branes span, in one dimension fewer. Both descriptions are of the same stack of branes. One has gravity and an extra dimension. The other has no gravity and one dimension less. Maldacena proposed that they are not two approximate pictures of one object, but the same physics exactly, written in two languages. Everything happening in the gravitational bowl has a precise translation into the flat, gravity-free theory on the boundary, and nothing is lost in the translation either way. The claim is stronger than an analogy, so it needs stating in its full form. A universe with gravity, in a certain number of dimensions, is completely equivalent to a universe without gravity, living on its boundary, in one dimension fewer. Not similar. Not a useful approximation. The same theory. Every question in one having an exact answer in the other. The whole of a gravitating interior encoded on a lower dimensional edge. The word hologram comes from here, and this is the one place the word is earned rather than decorative. A hologram stores a three-dimensional scene on a two-dimensional film, and the depth is recovered when the light is read correctly. Here, the depth is a real dimension of space and gravity itself, both reconstructed from a theory living on the surface that has neither. The inside is not hidden behind the boundary. The inside is what the boundary says, spelled out in a language where gravity does not appear as a word. What makes this more than a beautiful suggestion is that it can be checked, and it has been, exhaustively. A hard problem in the gravity picture, strongly curved and unsolvable by direct means, translates into an easy problem in the boundary theory, weakly interacting and calculable. Work out the easy version, translate the answer back, and it matches what little can be computed on the gravity side directly. This has been done for thousands of quantities over more than 25 years by people trying hard to break it. It is held every time. The relationship also runs the useful direction, which is why physicists far from string theory now use it. Some quantum systems in the real world are strongly interacting and resist every ordinary method. Hot nuclear matter of the kind made in collisions, certain strange metals. Translate such a system into the gravity language, and a strongly coupled quantum problem becomes a black hole with a temperature, which is tractable. The answers are approximate, because the real systems are not the idealized ones the duality treats exactly, and how far the method can be trusted there is itself debated. But a tool born in a theory of quantum gravity is now used to estimate the behavior of matter that has nothing to do with gravity, and that is not nothing. The sentence the whole part has been walking toward is a short one. Anti-de Sitter space curves inward. Its cosmological constant, the number that sets how empty space itself curves, is negative. The universe we live in does the opposite. Since 1998, it has been measured, again and again, that our space is being pushed apart by a cosmological constant that is positive, small, and not going away. Our universe accelerates outward. Anti-de Sitter space holds inward. The signs are opposite, and the sign is not a detail. So the most complete and most tested statement string theory has ever made, the one exact bridge anyone has built between gravity and quantum mechanics, is a statement about a universe with the wrong sign of curvature. It is a real theory of quantum gravity, fully consistent, checked to exhaustion. It is a theory of quantum gravity for a place that is not here. There is a temptation to soften this, and the softening is where the popular account usually goes wrong. The claim that our universe is a hologram, that everything around you is a projection of information on a distant surface, is not what was proved. What was proved concerns a space with inward curvature that we do not inhabit. Whether anything like it holds for a universe with outward curvature, a universe like ours, is an open question that people have worked on for 25 years without a clean answer. The one place the bridge stands on solid ground is the one place we are not. The honest version is smaller and stranger than the headline. The idea did not come from nowhere in 1997, and two people had reached for it earlier. Gerard Hooft, in the early 90s, had argued from the black hole entropy formula that the information in any region must be describable on its boundary, since that is where the entropy lives. Leonard Susskind had sharpened the argument and given it its name, the holographic principle. Maldaceno's achievement was to turn a principle into a specific, calculable, checkable equivalence in one particular kind of space. That the one kind of space where it could be made exact is not our kind is the discomfort this whole part rests on. The tools required, the branes, the supersymmetry, the special geometry, all cooperate in anti-de Sitter space and fight back in a universe like ours. The place the mathematics works cleanly is not the place we are standing, and moving the result from there to here is the unsolved problem, not a formality. What was one is still enormous, and it is the deepest thing to come out of 50 years of this. Gravity and quantum mechanics, the two descriptions that opened this whole story by refusing to share a room, share one exactly, with a complete dictionary between them, in at least one mathematically real universe. That such a universe can be written down at all was not known before. It settles that the contradiction is not fundamental. It leaves open whether the resolution reaches the world we inhabit. And there was a further cost, hiding in the freedom the theory had gained. To describe any real universe, the 6 extra dimensions must be folded and pinned into a stable shape, and there turned out to be an almost unlimited number of ways to do the pinning, each producing a different universe with different laws. So, how many universes does the theory allow? And what does a number that large do to the meaning of the word prediction? The theory that was meant to have no choices in it turned out to allow more distinct universes than there are particles in ours, and the number is written as 1 followed by 500 zeros. That figure did something to the word prediction that the subject has never recovered from. It is the moment the promise from earlier, a theory with almost no dials, quietly inverted into its opposite. The trouble grows out of the folded dimensions. 6 of them have to be curled into a compact shape, and we saw that the shape's connectivity fixes the physics we observe. But a Calabi-Yau shape is not rigid. It has handles and passages, and the sizes of those handles, how wide each one is, how far around each passage reaches, are not fixed by the shape alone. Each is a quantity free to take a range of values, and each such quantity is a separate knob controlling some feature of the 4-dimensional world. A typical shape has hundreds of these knobs. Left free, they drift, and a drifting knob is a disaster, because it means the constants of nature drift with it, the strength of forces and the masses of particles sliding around instead of holding still. We met this problem in its smallest form in the Kaluza-Klein story, where the single leftover quantity, the size of the one extra dimension, had nothing to hold it in place. Now there are hundreds of them at once. Something has to lock them down, and string theory has the ingredient. Through the passages of the folded shape, certain fields can thread, the higher dimensional cousins of a magnetic field running through a loop of wire. These threadings are called fluxes, and like so much else in the theory, they come in whole number amounts only, because the field has to close on itself as it passes through the handle, the same fitting around condition that quantized charge and momentum before. Each flux is an integer, and it stiffens the shape, holding the sizes of the handles at particular values instead of letting them drift. Thread 3 units through one passage and 5 through another, and the shape locks into a definite configuration with definite constants of nature reading out into the four-dimensional world. Change one integer, and a different configuration locks in, a different universe with different constants. The counting is the part that gets away from everyone. A shape with a few hundred passages, each able to carry any whole number of flux up to some ceiling set by consistency, has a number of configurations that is roughly that ceiling raised to the power of the number of passages. A modest ceiling and a few hundred passages give a number near 10 raised to the 500. Not 500 configurations. A 1 with 500 zeros written after it. That number needs holding against something, because 500 zeros slides past the ear as easily as 50. The observable universe contains around 10 to the 80 atoms. The number of seconds since the beginning is about 10 to the 17. Multiply every atom by every second and square the result and cube it, and you are nowhere near. 10 to the 500 is not a large count of the kind physics usually deals in. It is larger than every physical quantity in the visible universe multiplied together by hundreds of orders of magnitude, and it is a count of possible sets of physical law. The full mechanism for locking the fluxes and getting a universe with the right sign of curvature was assembled in 2003 by Shamit Kakru, Renata Kalosh, Andre Linde, and Sandip Trivedi, and it is known by their initials. It fixed a real problem, the drifting knobs, and in fixing it, it turned the drift into a vast catalog of stable, discrete choices. The knobs stopped sliding. In exchange, there were more settings for them than anyone could ever survey. This collection of possible universes acquired a name, the landscape, and it changed what asking string theory a question could mean. Ask it for the mass of the electron and it does not answer. It says the mass of the electron depends on which point in the landscape you are standing at, and it does not tell you which point that is. The constants that the theory once seemed poised to derive from nothing became a return address, a label for a location among 10 to the 500 rather than a consequence of the theory itself. A framework that predicts almost anything predicts nothing, and that is the plain form of the objection. The original hope had been sharp. 2 inputs, no free dials, and out the other end the constants of nature forced to be what they are. The landscape kept the 2 inputs and then hid 500 dials inside the folded dimensions, and every constant the theory was supposed to explain became a coordinate instead. The word prediction, in this setting, no longer means what it means everywhere else in physics. There is a way of reading this that is not surrender, and it turns on a single successful guess. Among the constants that vary across the landscape is the cosmological constant itself, the tiny outward push measured in 1998. Its measured value is famously strange, not 0, but smaller than the natural expectation by 120 orders of magnitude, a 1 preceded by 120 zeros in the denominator. No mechanism had ever explained why it sits at that fantastically small but non-zero value. In 1987, before the landscape and before the measurement, Steven Weinberg tried a different kind of argument. Suppose the cosmological constant takes many values across many regions, he reasoned, and ask which values allow galaxies to form. Too large and positive, and space flies apart before matter can gather into galaxies, and no observer exists to measure anything. Too large and negative, and space recollapses too soon for the same reason. Only a narrow band around zero permits structure, and therefore observers at all. Weinberg predicted, from this reasoning alone, that the cosmological constant should be found near the upper edge of that habitable band, small but not zero, within a factor of a few tens of where the measurement 11 years later came to rest. He had no landscape to justify the many values. The landscape, arriving later, supplied exactly the many values his argument had assumed. Whether that counts as a triumph or a confession is the question the whole subject splits on, and both readings are serious. On one reading, a real prediction was made, ahead of the data, and it came true, and the landscape is the physical reason the prediction works. On the other, an argument that says the constant is whatever it must be for us to exist has stopped explaining the constant and started explaining us, which is not the same job and may not be physics. The uncomfortable part is that the two readings cannot be separated by any calculation. They differ only in what a person is willing to accept as an explanation. If a number comes out right because only that value permits an observer to ask, has the number been explained, or has the question been changed? Physics had not before been forced to decide where that line falls, and it is not agreed now. There is one more turn, and it is the reason this is not simply a story of a theory losing its nerve. The landscape did not stay a lonely embarrassment for string theory. A completely separate line of work, in cosmology, had arrived at its own version of many universes, for reasons that had nothing to do with strings, and the two pictures fit together disturbingly well. If regions with different physics exist as real places rather than mere possibilities, something has to make them, spin them off, populate the landscape with real universes rather than a list of options on paper. That making machine already existed in another branch of physics, proposed to solve a different problem entirely, and it turned the 10 to the 500 from a catalog into a population. So what was that machine? And how did a theory of the first instant after the beginning end up handing string theory the multitude it needed? The machine that turned 10 to the 500 possibilities into 10 to the 500 real places was not built for string theory, and its inventor was trying to fix the beginning of the universe. He solved 3 separate problems with one idea, and the idea would not switch off once started. That refusal to switch off is what makes the universes real rather than hypothetical. Start with the 3 problems, because the fix only makes sense against them. The Big Bang, as understood in the 1970s, was a superb description of an expanding, cooling universe that left 3 things unexplained, and each was a matter of a number being wrong by a wide margin. The first was flatness. Space, on the largest scales we can measure, is very close to geometrically flat, meaning parallel beams of light stay parallel, and the angles of a great triangle add to 180 degrees. The trouble is that flatness is unstable in an ordinary expanding universe, the way a pencil balanced on its tip is unstable. Any tiny curvature early on grows as the universe expands. So to be nearly flat now, the universe had to have been flat at the start to something like 60 decimal places. A number that finely tuned, with no reason behind it, is the kind of thing that keeps physicists awake. The second was the horizon problem, and it is stranger. Look at the oldest light in the sky, the glow left over from when the universe first turned transparent, and it has almost exactly the same temperature in every direction, to a few parts in 100,000. That sameness should be impossible. Two patches of sky on opposite sides were never in contact, not once since the beginning, because light has not had time to cross between them. Nothing that never touched should match that precisely. Yet the whole sky agrees on its temperature as though it had been stirred. The third was a prediction, not an absence. The best attempts to unify the forces, the grand unified theories from a few parts ago, said the early universe should have produced heavy magnetic monopoles in quantity, isolated north poles and south poles, one kind of charge without its partner. They should be everywhere. None has ever been found, not one, in any experiment built to look. A single detector in 1982 recorded one candidate event on a Valentine's night, and in more than 40 years since, nothing has ever confirmed it. One unrepeated flicker against a prediction of swarms. 3 problems, and they look unrelated. A universe too flat to be natural, a sky too uniform to be possible, a swarm of particles that should exist and does not. In 1980, Alan Guth found that one move answers all 3 at once, and the economy of it is the reason it was believed. The move is a burst of expansion, brief and violent, in the first fraction of a second. Not the steady expansion of the ordinary Big Bang, but a doubling, and another doubling, and another, the size of a region multiplying again and again in a vanishing sliver of time, growing by a factor of 10 to the 26 or more before it stops. Guth called it inflation. The numbers are hard to hold, so one comparison helps. In the sliver of time inflation runs, a region smaller than a single proton is stretched to something larger than a grapefruit, and in ordinary terms, that is a patch of space growing by more in an instant than it has grown in the 14 billion years since. Watch how one idea clears all 3 problems, because that is where its force comes from. Take any curved surface and blow it up enormously, and the piece you are standing on looks flat, the way the ground underfoot looks level though the earth is round. Inflation stretches any initial curvature until the observable universe is flat to far better than we can measure, and the flatness problem is gone. The horizon problem goes the same way in reverse. The patches of sky that seem never to have touched did touch before inflation, when the whole visible universe was packed into a region small enough for light to cross easily. They reached a common temperature then, in contact, and inflation afterward flung them apart to opposite ends of the sky, carrying their agreement with them. The uniformity is a memory of an intimacy that the expansion later hid. And the monopoles are simply diluted away. Whatever was made before inflation, however densely, gets spread across a volume so vastly enlarged that the density falls to almost nothing. The monopoles were not destroyed. They were thinned until, on average, fewer than 1 remains in the entire region we can see. 1 mechanism, 3 problems. No new parameters tuned to make it work. That is the kind of result that persuades, and inflation was accepted quickly, and it has since passed real tests, predicting the precise pattern of ripples in that oldest light before the ripples were measured in detail. But Goth's own first version had a flaw he named in the same paper that proposed it. His inflation, once begun, did not know how to end cleanly. The repair came from André Linde, and independently from Andreas Albrecht and Paul Steinhardt, and it is the repair that matters for everything after. Instead of inflation ending everywhere at once, it ends in patches. One region stops inflating and settles into an ordinary universe, expanding gently, cooling, forming galaxies. The space around that region, though, is still inflating, and it inflates faster than the settled patches can eat into it. Follow that forward and it does not stop. The inflating background keeps spawning calm bubbles, each one a universe settling out, while between and around them the inflation races on, making room for more bubbles faster than the bubbles form. Once inflation starts, in this picture, it never fully ends. It continues somewhere always, budding off pocket universes without limit, into the past very likely, and into the future without end. The name for this is eternal inflation. Now the two threads of this whole story cross. String theory had produced a landscape, 10 to the 500 possible sets of physical law, and left them as a catalog, a list of foldings on paper with no reason to think more than one was ever built. Eternal inflation is a machine for building them. Each bubble that settles out of the inflating background can settle into a different point in the landscape, a different folding of the hidden dimensions, a different set of constants. The catalog becomes a population. Two frameworks, developed for entirely unrelated reasons, one to reconcile gravity with quantum mechanics and one to fix the early universe, fit together at exactly the seam where each was incomplete. String theory had many possible universes and no way to realize them. Inflation had a way to realize many universes and nothing to say about what laws each would carry. Set side by side, each supplies precisely what the other lacks. There is a reading of that fit that draws people in, and one that should give pause, and the difficult thing is that they are the same observation. When two independent theories dovetail this cleanly, it can mean they are both circling a shared truth. It can also mean that two speculative structures, neither yet confirmed, have been leaned against each other, so that each appears to hold the other up, when in fact, nothing underneath either has touched the ground. A confirmed theory resting on a confirmed theory is a building. Two conjectures propping each other are a scaffold with no wall behind it. Which of those this is cannot be settled from inside, and that is not a rhetorical flourish. Eternal inflation, taken seriously, predicts that most of reality is regions we can never see, carrying laws we can never measure, and a claim about the permanently invisible is a hard thing to hold to the standard the proton decay experiment met. Some physicists take the multiverse as the plainest reading of theories they already trust. Others take its unreachability as the point where this stopped being physics. This is the exact fault line the field runs along, and no measurement now in view crosses it. So the theory had gained a multitude of universes and, with it, the deepest objection it has ever faced, that it may have talked its way past the possibility of ever being wrong. The answer to that objection, when it came, did not come from cosmology. It came from the mathematics turning around and forbidding things. For 40 years, the loudest complaint against string theory was that it never forbade anything, and then it forbade something specific about a number being measured right now. The complaint was fair for most of that time. A theory that permits 10 to the 500 universes has not, on its own, told the world what it must find. The swampland is the attempt to change that, and it aims at exactly the freedom the landscape had bought. The idea starts with a distinction that sounds like wordplay and is not. The landscape is the set of universes string theory can produce, the 10 to the 500 stable foldings. Around that set, far larger, is the space of universes that look perfectly reasonable on their own terms, with sensible particles and forces, obeying every rule of quantum theory, and yet cannot be produced by any consistent theory that includes gravity. Qumran Vafa named that outer region the swampland. In 2005, reasonable-looking theories that gravity quietly forbids. The claim behind the word is strong, and it took time to see how strong. Most quantum field theories, written down on their own, look consistent. You choose your particles, choose the strengths of their interactions, and check that probabilities behave. The swampland proposal says that once gravity is added, most of those theories stop being possible, not because of any flaw visible from inside them, but because no complete theory of quantum gravity can ever contain them. The landscape, vast as it is a small island in a far larger sea of things that cannot be built. The work of the swampland is to find the fence, to state the conditions that separate the island from the sea. These conditions are called conjectures, and the word is exact, because none is proved from first principles. Each is read off from the pattern of what string theory does and does not produce, across every example anyone can construct, and then proposed as a general law. They are educated readings of a large body of evidence, not theorems, and the people making them say so. One of them is easier to feel than the rest. It concerns the size of the extra dimensions, and it says that a folded shape cannot be held stable at a large size for free. Push the compact dimensions toward being large, and a tower of those Kaluza-Klein copies from earlier comes crashing down in mass, growing light, flooding the theory with new particles until the original description falls apart. Written out, the lightest of them drops in mass exponentially as the size grows, so a large extra dimension cannot hide quietly. It announces itself with an avalanche of new states. The one that reached the daylight concerns empty space. Our universe is filled with a small positive energy, the cosmological constant, driving the acceleration measured in 1998. A space with a constant positive energy of that kind, holding still forever, is called de Sitter space. The swampland conjecture about it, put forward in 2018 by Vafa with George Obide, Hiroshi Oguri, and Lev Spodinaiko, says something a physicist can check. A stable de Sitter space may not sit in the landscape at all. It may belong to the swampland. If that is right, the consequence is sharp, because we appear to live in something close to de Sitter space. The conjecture does not say the acceleration is fake. It says the energy driving it cannot be a true constant, fixed for all time. It has to be something that changes, however slowly, a field gently rolling downhill rather than a number frozen in place. The dark energy, in this reading, must be dynamical. That is a statement the sky can rule on, which is what makes it different from everything before it in this story. A true cosmological constant has one value and holds it forever, so its strength today equals its strength a billion years ago exactly. A rolling field weakens as it descends, so its strength today is measurably less than it was in the deep past. Point a survey at enough distant galaxies, measure how the push has changed across cosmic time, and the two possibilities separate. The awkward part, which the theory's own people are the first to raise, is that this same conjecture sits in tension with the mechanism from the last part. The KKLT construction was built precisely to produce a stable de Sitter space, a frozen positive constant, inside string theory. The de Sitter conjecture says that may not be allowed. Most known versions of KKLT on the swampland reading fall on the wrong side of the fence, into the sea rather than the island. Two groups of respected physicists using the same theory disagree about whether our own kind of universe can be built in it at all, and the disagreement is live. The disagreement is not a weakness to hide. It is the first time in 50 years that string theory has generated a fight about a specific, near-term, measurable number. For most of its history, the objection was that no measurement could touch it. Now, two camps within the theory are staking opposite claims on what a galaxy survey will show, and the survey is running. Because the survey is running. A telescope in Arizona, feeding light down 5,000 thin optical fibers, has been mapping the positions of millions of galaxies to reconstruct how the expansion has changed across the age of the universe. In 2024 and again in 2025, its collaboration reported that the data prefer, at a moderate level of confidence, a dark energy that has been weakening rather than holding constant. The push may have been stronger in the past than it is today. The result is not settled, and the caution matters as much as the number. The preference for changing dark energy sits at a few standard deviations, which in this field is interesting and not yet conclusive. Many cosmologists expect the signal to soften as more data arrive and drift back toward a plain constant. It has happened before, to results that looked more secure than this one. The measurement is a hint, held up plainly as a hint, not a verdict. But consider what kind of hint it is. A conjecture drawn from the deep structure of string theory said, before these measurements sharpened, that the dark energy should not be constant. A survey with no interest in string theory then found the first tentative sign that it might not be. Vafa has pointed out that the direction of the data matches what his conjecture required, in sign and roughly in size. For a framework accused for 2 generations of predicting nothing, a prediction pointed at an ongoing measurement is a change in kind. The reversal is the thing to hold on to here, and it deserves saying plainly. Through most of this story, string theory absorbed whatever the world showed it, adjusting, folding in each new fact after it arrived. The swampland runs the other way. It says from the mathematics alone that certain worlds are forbidden, and it says so before the measurement, and it lets the measurement decide. That is the posture the whole enterprise had been accused of never taking. There is no guarantee it will survive the taking. The conjectures may be wrong, misread from an incomplete set of examples. The de Sitter statement in particular is disputed by serious people who think stable de Sitter space is perfectly constructible. And the data may firm up in the other direction, toward the constant the conjecture forbids, in which case this version of the swampland is finished, cleanly, by observation. That is not a failure of the program. It is the program working the way a physical theory is supposed to. And the measurement that would decide it turns on the same quantity that has haunted the theory since the beginning, the size of a hidden dimension refusing to hold still. Only now the refusal is not a bookkeeping nuisance in a 50-year-old paper. It is a proposal about what a laboratory on Earth might see. So where exactly is that laboratory, and what is it about to weigh? The most promising test of a 50-year-old theory about the smallest distance in physics is being attempted right now on a tabletop. And the thing it is looking for is about the width of a human cell. That sentence should not be possible. Everything in this story has pointed toward energies no machine will ever reach. And here is a version of the same idea being weighed on a torsion balance in a university basement. The path to that table runs back through the size of a hidden dimension, the quantity that has refused to hold still since the 1920s. The swampland conjecture from the last part said, a large extra dimension cannot stay hidden for free, that pushing it larger floods the theory with light particles. Qumran Vafa and his collaborators took that seriously and asked a precise question. Given the measured value of the dark energy, tiny and positive, how large does the conjecture force one of the extra dimensions to be? The answer, worked out around 2022, was startling in a way none of the earlier numbers had been. Every previous scale in this story lived near the Planck length, 20 powers of 10 below anything reachable. This one did not. The relationship ties the size of the dimension to the dark energy by a specific power law, and when the measured dark energy is put in, the dimension comes out somewhere near a micron, a millionth of a meter. A micron is not an abstract size. It is roughly the width of a small bacterium, a fraction of the width of a hair, a thing an ordinary microscope can see. The proposal, called the dark dimension, is that one of the extra dimensions the theory has always needed is not folded down near the Planck length at all, but is enormously larger, sitting at a scale we can nearly touch. That should sound alarming, and the alarm is the right instinct. An extra dimension, a micron across, seems like something we would have noticed. The reason we would not have is the same reason Oscar Klein gave a century ago: sharpened. Only gravity is free to reach into the extra dimension. The particles of matter, the electrons and quarks and light itself, are stuck to the 3 dimensions we know, confined to the surface, in the language of the branes from earlier. Gravity alone leaks into the extra one. So the test is a test of gravity, and only gravity, at short distances. Newton's law says the pull between 2 masses falls off as the square of the distance between them, and it has been checked to enormous precision at every scale, from the planetary down to the everyday. But if gravity can spread into an extra dimension once 2 masses come within a micron of each other, its falling off should change from the square of the distance to a steeper power, because the force lines have one more direction to spread through. Below a micron, gravity should get stronger, faster than Newton allows. That is a laboratory question, and it is being asked. The instrument is a torsion balance, one of the oldest and most delicate tools in physics, a design not far from what Henry Cavendish used to weigh the Earth in 1798. A small test mass hangs from a fine fiber near another mass, and the faint gravitational pull between them twists the fiber by a minute angle. Measure the twist, and you measure the force. Groups doing this, at Washington and at Stanford and elsewhere, have pushed the measurement of Newton's law down to separations well below a millimeter and are working their way toward the micron. The gap left to close is not large, and that is what makes this the sharpest thing in the whole story. Current experiments have confirmed ordinary gravity down to a few tens of microns, with nothing unusual seen. The dark dimension proposal lives just below that, and closing the remaining factor of 10 or so in reach is a matter of better isolation, quieter apparatus, patience, not of building a machine the size of a solar system. A serious test could come within years, from a device that fits on a bench. There is a second signature, and it doubles the interest. If gravity lives in a dimension a micron wide, then the graviton, spreading through that dimension, comes with a tower of heavier copies of itself, the same Kaluza-Klein ladder we met in the 1920s, now with rungs light enough to matter. Those copies would be massive, feebly interacting particles produced in the early universe and drifting through space ever since. They behave, in this proposal, exactly like dark matter, the unseen mass that holds galaxies together. The extra dimension would furnish both the dark energy that set its size and the dark matter that fills the sky from one piece of geometry. The honest caveat has to sit right beside the promise, because this is a scenario, not a result. The dark dimension is one reading of one conjecture, and the conjecture itself is disputed by careful people. The measured dark energy might yet turn out to be a true constant after all, which would pull the ground from under the whole construction. And the tabletop experiments might reach the micron and find nothing but Newton's law, holding as it always has, which would close this door cleanly. That is not a weakness. It is the first time in 50 years that a specific number from this theory has been within a decade of a yes or a no. Whatever the balance reads, something has already been found, and it is time to say plainly what 50 years really produced. The theory of everything did not arrive. Nobody has written the equation that governs M-theory. No experiment has confirmed a string, and the framework permits so many universes that it names none of them as ours. By the standard it set for itself, the standard the proton decay experiment met and passed, string theory has not succeeded. And along the way it was right about a startling number of things it was never aiming at. It contained gravity when it was trying to describe the nucleus. It counted the hidden states inside a black hole to the last factor when nobody had been able to. It built the one exact bridge anyone has ever constructed between gravity and quantum mechanics in a universe not quite ours. Its tools now estimate the behavior of hot nuclear matter in real collisions, a subject that has nothing to do with strings. There is one result that shows the pattern better than any other. In studying how the folded shapes could differ, mathematicians using string theory found that certain pairs of completely different shapes give identical physics, a relationship called mirror symmetry. Using it, they solved a problem in pure geometry that had defeated mathematicians for a century, counting the number of curves of each kind that can be drawn inside a particular surface. The physicists handed the answer to the mathematicians who had not asked and could not yet prove it, and it was correct. The count of curves of the lowest kind on that surface had been known since the 1800s, a number in the low thousands. The next count up, which no one had ever managed, came out of the string calculation in the hundreds of thousands, and the one after that in the hundreds of millions, and each was later confirmed by hand. So a theory built to explain the atomic nucleus, which failed at that, turned out to solve a problem in 19th century geometry, by way of a symmetry between six-dimensional shapes nobody can see. That is the shape of the whole 50 years, in one sentence. Wrong about what it was built for, right about things no one thought to ask it. The name was the mistake, not the work. A theory of everything was never what this was, and calling it that set it up to be judged as a failure for not being a thing it could not have been. What it turned out to be is a mine, a source of true and unexpected results in gravity, in geometry, in the physics of matter, arriving from a direction no one was watching. That is enough to carry us back, at the end, to the only laboratory any of this has ever certainly touched, which is the one you are lying in. The contradiction this whole story began with has not been resolved, and it is closer to you than any laboratory. It is in the room. It is in the body lying in the room. Think back to where we started. Two small masses on a table and the gap between them closing. The pull grows as the gap shrinks, and nothing in the arithmetic ever says stop, and it was that refusal to stop, that pull climbing without limit as the distance falls toward nothing, that opened the whole search. Everything across these hours, the strings, the extra dimensions, the branes, the holograms, the landscape, was an attempt to say what happens in that last unimaginable closeness where the two descriptions of gravity we trust stop agreeing. That last closeness is not somewhere far away. It is inside every atom you are made of. The particles in your body are held in their shapes by quantum rules, the same rules that describe the nucleus and the electron and the light in the room. And that same body is held against the bed by gravity, by the curvature of space and time that Einstein described, the pull of a whole planet gathered gently under you. Both descriptions are running, right now, in the same few pounds of matter. The quantum rules are keeping every one of your atoms intact, moment to moment, without pause. The gravitational description is holding you exactly where you are, unmistakably, with a force you can feel as the weight of your own limbs against the mattress. Neither one is approximate. Neither one is somewhere else. And nobody can write the equation that contains them both. Not because the two are far apart, but because they overlap perfectly, here, in you, and the overlap is exactly the place where the mathematics stops working. The energies in a resting body are far too gentle to force the question, so the two descriptions sit side by side without ever colliding, each doing its work, neither needing the other, in the same cubic handful of space. That is the honest ending, and it is a stranger one than a solved theory would have been. For 50 years, the search for a theory of everything reached toward the edges of reality, toward the first instant after the beginning and the centers of black holes, toward energies no machine will ever make. And the one place the contradiction truly lives, the place where quantum mechanics and gravity are both undeniably true at once, is not out there at all. It is under your own weight, tonight, in the quiet. The theory of everything was never going to hand you the universe in a single equation. That was the wrong thing to have wanted, and the wrong thing to have promised. What the search found instead was smaller and better, a long chain of true things discovered by accident, gravity falling out of a theory of the nucleus, the inside of a black hole counted from the outside, a bridge between the two great descriptions standing in a universe not quite ours, a hidden dimension that a table in a basement may soon weigh. None of it is the final answer. All of it is real. And the question it was chasing is still open, which is not a sad thing to carry into sleep. It means the universe still has this held in reserve, a real unknown sitting quietly inside ordinary matter, waiting, in no hurry, for someone to see it plainly. The people who spent their lives on it did not finish it. They were never going to finish it. They laid stones for something none of them would see completed, and that is one of the more common ways that lasting things get built. There is a symmetry in that, and it asks nothing of you to see. The search went outward as far as thought can go, to the beginning of time and the heart of a collapsed star, and it came back around to the simplest fact in the room, which is that you have weight and that you can feel it. The reaching and the resting turn out to be about the same thing. The pull between two masses, Closing a gap is where the whole question started, and it is also what is settling you into the mattress at this moment, unhurried, exact, the oldest force there is doing the quietest work it does. You do not have to hold any of it tonight. The strings and the dimensions and the branes will keep without you. The two descriptions will go on running in every atom of you, whether or not anyone is thinking about them, the way they have since long before there was anyone to think. Thank you for spending this quiet stretch of the night here, following a hard idea all the way through to the place where it plainly runs out. There is something restful in a question that stays open, that asks nothing of you, that simply is what it is and lets you rest beside it. Let the weight settle. Let the pull that started this whole story do the one thing it has always reliably done, and hold you gently where you are. Sleep well.